Patil, welcome you all for today's FDP session on hybrid vehicles. A very good evening to one and all. I, Dr. Vandana Patil, welcome you all for today's FDP session on hybrid vehicle. It is my great pleasure to introduce our speaker, Mr. Rakesh Mullik sir. Sir is currently working as a Deputy General Manager at Automotive Research Association of India, ARI Pune. Sir has completed his Masters from Savitribai Phule Pune University, also pursuing PhD from VIT University, Vellore. Sir has published many research papers in various national and international conferences as well as journals. So, without any delay, I would like to invite Mr. Rakesh sir to address the participants. Over to you, sir.
Yeah, thank you, ma'am, and good afternoon to all. So, please tell me, ma'am, I'm sharing my screen, so whether it is visible to you so that I can proceed. Can you see the screen, ma'am?
No, sir.
Okay.
Yes, sir.
Yeah,
Just make the slideshow, then okay, sir.
yeah, okay. So, good afternoon to all participants, and I'm thankful for D.Y. Patel College of Engineering for giving me this opportunity. So, title of my topic is actually hybrid electric vehicles, but I will be covering electric vehicles, hybrid electric vehicles, and fuel cell hybrid electric vehicles. We will see configurations and the future trends. Uh, Here, if you see, now I will first briefly introduce about ARAI. So ARAI is an autonomous premium self-supported R&D institute. We are affiliated to Ministry of Heavy Industry, Government of India. So we are established at 1966 and situated in Pune. Okay, so there are different divisions. I'm not going into those details now. All those information you can see from our website. So without wasting time, I will directly switch to our topic. Okay. So present power plants of transportation. So if you see nowadays we are using automobile which are either powered by a gasoline or diesel or CNG and so on. So we are having dependency on fossil fuels and which we are importing mostly from the Gulf countries, right? And if you see automotive industry, so it is the biggest economic force in India or across the globe, you can say. So it is giving jobs to majority of the people, approximately most of the more than 50% of the industry. You can see it is related to automobile and all. So environmental concerns. So mostly we are having few environmental concerns because of increasing population of the vehicles on road. So mostly CO2 emission. Okay, so it is known as a greenhouse gas. So greenhouse gas emission is coming out from transportation is approximately 31.1%. Then more than two-thirds of this transport is related to GST, is related to again road transport. If you see this pie chart, which is over here, if you see amongst all, road transport will give us a 72% of the CO2 emissions. Okay, so it is related to the vehicles plying on the road. And if you see the India, so we are having BS2, BS3 vehicles, even though we have a mandate now from this April 2020 to go with the BS6, but still majority of the population are of BS3, BS4, BS2 and so on. So this is actually of serious concern. And every year or after every few years, government of India across the globe, we are having certain strict regulations on CO2 emission. Okay, so now if you see this graph, I have some data of 2020 as well. So if you see 2012, CO2 emissions were targeted 120 gram per kilometer, less than that. And now the target will come, it should be less than 100 gram per kilometer. Secondly, the depleting oil sources. So it has been predicted that oil sources will last for next 40 to 50 years only. So it is one of the major concern, and that's the reason now our honorable Prime Minister also on 15th of August they have asked or they have guided us to go for a hydrogen economy. So hydrogen is now emerging as a alternate fuel. So need and motivation for going towards the alternate fuels is stringent emission norms, fuel economy, so that we can lower the CO2 emissions, then higher specific power from the power plant, high torque backup, improved NVH, enhanced durability, high power to weight ratio. Okay. So life cycle for any vehicle development or any product development you can see. So it is actually a typical life cycle. So I'm not going into those details. So if you see a target specification, then powertrain specification, and component specification, design and development. If anything goes wrong, again we have to go for the conceptualization, then testing, prototype development, and start of production. Okay, so it is a conventional life cycle for any of the product, not only the automobile. Then coming back to our topic, hybrid electric vehicles. So hybrid electric vehicles are categorized into different topologies or different configurations. First is a micro hybrid electric vehicle. Okay, so micro hybrid electric vehicles are those which are having only a start stop kind of technology. Means whenever you are having at a, say you are standing at a signal, and if you remove your foot from accelerator pedal, vehicle's engine automatically will be shut off, and whenever again we are pressing the accelerator pedal, engine will start again. Okay, so it is known as a micro hybrid electric vehicle. If you have seen Mahindra Scorpio, at the back side it has been written micro HEV, so it falls under a start stop kind of hybrid electric vehicle. Then comes mild hybrid electric vehicle. So before going into further classification, we will see what is DOH, degree of hybridization. So power of electric motor divided by total power, that is power of IC engine and power of electric motor. Okay, so if we say 100% degree of hybridization means what? Power of IC engine is 0 and power of electric motor is 100, and 0% degree of hybridization means power of electric motor is 0, 100% that vehicle will be a IC engine based vehicle. So anything lying between 0 to 100 is a hybrid electric vehicle. So in case of hybrid electric vehicles, when we say hybrid electric vehicles, it might be a IC engine plus electric motor or fuel cell plus electric motor. So we will see plus first hybrid electric vehicles, that is IC engine plus electric motor, then we will see fuel cell. Then coming back again here, full hybrid electric vehicles. Whenever we are having a degree of hybridization 30 to 50%, it is known as a full hybrid electric vehicles. So we will see in detail what exactly the full hybrid electric vehicle is, and the plug-in hybrid electric vehicle. So plug-in hybrid electric vehicles, you can say these are some sort of electric vehicles only. Means those are having IC engine plus bigger size of battery. Means apart from hybridization, we are providing them a external plug-in port so that we can charge the battery as like in electric vehicles, and it will go in a hybrid mode as well. So this is actually a broad level classification of hybrid electric vehicles. So it is actually a roadmap. Ultimately, we have to go towards electrification or fuel cell electric vehicles, I will say. So presently we are having IC engine electric vehicles right now. Then we will move towards hybrid electric vehicles, plug-in hybrid electric vehicles, and then ultimately to fuel cell electric vehicles. So why we will be going to fuel cell electric vehicles, that I will let you know in subsequent slides. So we'll start with electric vehicles. So few of the topics I will just touch in the interest of time, and few we will go in detail. So history of electric vehicles, yes, you can refer any of the textbook or any internet sites, you can get this. So electric vehicle, actually it is not a new technology. It has been invented long back in 1881. But at that time, size of the battery was very less. Battery technology was not there. Motor technology was not that much of matured. If you see here, 0.1 HP and that to DC motor. So nowadays trends is toward AC motor and so on. So if you see, approximately weight was also very high at that time. It was a tricycle actually, and speed was having a limitation, range was having a limitation. Few limitations still persists even the technology have advanced. Then comes a general EV configuration. So these few slides we will just go through. So if you see here, mechanical transmission, in case of electric vehicles, multi-speed gearbox may not be required. Why? We will see its answer in subsequent slides when we see hybrid electric vehicles in detail. So we will be having a electric motor drive, energy source, that is a battery. Maybe it is a DC source. So maybe lithium ion battery or lead acid. Nobody is using lead acid for electric vehicles nowadays, but lithium ion battery, there are different chemistries: lithium ion phosphate, lithium manganese cobalt, and salt meter battery, etc., etc. Then comes a control strategy. Yeah, so you have developed, suppose, a layout, but efficient control strategy development is very much important over here. So vehicle controller actually is a brain of any hybrid electric vehicles or electric vehicles or fuel cell electric vehicles. We will see this in detail. Then electric vehicle controller, what it does, it takes the signal from the wheels, sometimes what exactly the power I'll be requiring for negotiating a certain gradient or negotiating a tractive effort requirement at the wheels. So those feedback have been taken by the vehicle controller, and it sees how much is the state of charge available inside the battery, and accordingly efficient energy management system will be there. It divides the power between the auxiliary power system, then the main motor controller, then electric motor, and so on. So we'll see all those things in detail. There are different EV configurations. For example, motor, clutch, gearbox, differential. It is actually, you can correlate with the conventional ICE engine powered vehicles layout. Then motor, gearbox, and differential. Sometimes in case of electric vehicles, you need not require a clutch, because here you are having a wide speed and torque band available with the help of the typical characteristic of electric motor that we are going to see in subsequent slides. Then you can mount this all those components in a transverse direction instead of longitudinal direction. Then motor and the final gear ratio like this, it is called as a semi floating kind of concept. Then we can put a final gear reduction inside the wheel, motor adjacent to it, or we can directly mount the motor inside the wheel. If you see small two wheelers, electric two wheelers, generally we are using this kind of configuration. Motors are lies inside the wheel, so it is known as a wheel hub motor. Okay, so this slide is very important before moving ahead. So it is actually a typical speed and torque characteristic curve of a motor. So if you see here, at the lower RPMs, we are having plenty of torque available with the help of motor. Now before seeing this curve, now we will see first what is a conventional ICE engine characteristic curve. Yeah, just a second. Okay, so typical ICE engine characteristic curve. So if you see, ICE engine is having particular torque or maximum torque at a particular RPM and maximum power at a particular RPM. So at the lower RPMs, you are not having any power, okay, and not having any torque. I can say. So if you see the idling RPM of engine, whenever I am putting my ICE engine vehicle in a neutral, it may be, or engine may be rotating at 8000 rpm, 1000 rpm, 1000 rpm, or 1200 rpm, like that. So we are not having any torque at a lower rpm, and we are having a maximum power at a particular rpm where torque is not maximum. It is actually a typical ICE engine characteristic curve. Okay, so that is the reason if you want to start your vehicle from a zero speed, okay, 0 km per hour, if I want to start from zero, but I am not having any torque available at that slower speed, because speed is directly in relation with the ICE engine RPM, and at a lower RPM I am not having any torque. So that is the reason we must introduce a gearbox or gear ratios. So 1, 2, 3, 4, etc. That again we are going to see in subsequent slides. But at this moment, you keep in mind this is a torque and speed characteristic curve of an engine. Similarly, it is a BSFC curve. Means BSFC, brake specific fuel consumption. How much fuel my engine is going to consume for providing me a particular power. It is known as a specific fuel consumption. Okay. So now compare that ICE engine characteristic curve with this motor characteristic curve. If you see here now 0 RPM or very less RPM, 5 RPM, 10 RPM, etc. So we are having a maximum torque available because the flux is constant at that time. And whenever we are going to increase the speed of this motor, flux going to decrease, or rather I can say torque is going to decrease. And there comes a particular point where power becomes constant. Initially, power is not there. We are having a maximum torque, which is the requirement of any kind of electric, any kind of vehicle. So at the lower RPM, we will be requiring a maximum torque for starting off vehicle from 0 km per hour. So typical characteristic curve of a motor provides us that freedom, because it provides us a maximum torque even at a very less speed, motor speed, which is corresponding again to vehicle speed. Okay. So when we are going to increase the speed, voltage increases, and after that voltage becomes constant, hence power becomes constant. And there comes a particular point from which torque becomes decreasing trend, or torque decreases and power becomes constant. So that point or velocity of the motor, velocity of the vehicle corresponding to this point is known as the base speed of the vehicle, and the motor speed is known as the base speed of a motor. So this is actually a typical characteristic curve of a motor. Okay, and if we go on reducing, if we go on increasing gear ratios, or if we are going to, if we are changing the gear ratios, for example, gear ratio 2, then it will be having particular power and torque combination. Okay, so in case of electric motors, generally multi-speed gearbox is not required. The reason is that we are having maximum torque available with us even at a lower speeds of the vehicle. Okay, so this is very important slide to keep in mind. Then whenever I want to develop a control strategy, okay, so development of control strategy is one of my PhD research topics. So I'm showing some of the slides to you later on. So if you see here, the torque speed characteristic curve again, and whenever I will be driving my vehicle on highways, so I will be not requiring the torque, so I will shift my motor characteristic point in such a region where I'll be getting a maximum power. Okay, so suppose here I am getting a maximum or constant power because I am not requiring any torque, because I am driving my vehicle on a highway. So according to the conditions, my vehicular control unit, in earlier slide I have shown you vehicular control unit. So depending upon the speed requirements and depending upon the traction requirement at the wheels, so you might be knowing what exactly the requirement of traction, rolling resistance plus aerodynamic resistance plus gradient resistance. It will give us a maximum tractive effort required for the vehicle for particular requirement of the vehicle, and we have to design or decide a power plant operating characteristic curve point, means torque point and the power point, in such a way that at that point we should negotiate that particular resistance. Okay, so whenever I'm driving my vehicle on a ghat section, so I'll be requiring maximum torque. So vehicular control unit adjust the current and voltage in such a way that my operating point of a power plant lies somewhere over here, where I'll be getting a maximum torque. Whenever I'm driving on a highway, traction requirement is less, vehicle control unit again comes into picture. It changes the operating points in such a way that there will be maximum power available from the power plant, and so on. So some of the equations, I'm not going into those details. Some of the electric vehicles, even in India now, you can see Tata Nexon is there, Tigor is there, Mahindra E2O is there. So many electric vehicles are coming into picture or coming on the road. Only the drawback of these electric vehicles, so the drawback which we're having in 1881 still persists even though technology have improved. What is that drawback? First drawback is a cost. If you see, a two-seater vehicle is itself causing us a 20,000 USD, and the Teslas, so Teslas are more than 70,000 USD. So cost is one of the thing over here. Why? Because we are using a motor, then batteries are costly depending upon the chemistry. For example, lithium ion. So lithium is available in some of the countries or some of the part of the world, for example, Congo, China. So we have to import it. So cost associated with that. Then if we are going to a permanent magnet synchronous motor, so those are using rare earth magnets. The cost of the rare earth magnets is more. If you are thinking for using induction motor, for providing a particular power and torque, size of induction motor increases. Even though Teslas are having their patented technology on induction motor, so they have very lightweight induction motor, and research is going on in such a way that we can use a low speed, very high speed and low weight induction motors in which rotors are made of aluminum. Okay, so such things are going on. Then if you see, one of drawback, we don't have charging infrastructure in place. Even in Europe or in US, there is that much of infrastructure as compared to gasoline fuel stations is not available for electric vehicles. So that is one of the again drawbacks. So if you have read maybe couple of weeks or in last week, Tata Power have announced to install more than 1,000 stations for charging the electric vehicles across India in different cities. Yeah, so it is actually a very costly affair. So that is the reason this technology not went to that level where IC engines are there, but still it is now increasing market. If you see on roads, you can see plenty of the electric vehicles and so on. Even the two-wheelers, Ather Energy, Ola, and so many players are coming into market now. Now we will see hybrid electric vehicles. It is actually very brief about electrification. So before moving into hybrid electric vehicles, what are the basic technologies to improve fuel economy? Because why we are doing all those things? Because I have explained to you, scarcity of oil and pollution. So can our ICE engine technology has reached to that maturity level beyond which we cannot go? So what efforts we have taken for improvement of that vehicle fuel economy? So these are some of the points. Reducing vehicle resistances, as I explained to you. So aerodynamic drag. So we tried to reduce the aerodynamic drag by different types of designs of the vehicle, different types of designs of tires, for example, steel wire plied tires or tubeless tires, improving the transmission efficiency, reducing energy losses in the transmission, reducing rolling resistance. I have already explained you, lightweighting of the material. So all those things we did, so that if you see modern days vehicles are having much more fuel economy compared to those vehicles in 1980s and 90s. Then improving engine operating points or engine operating efficiency. What are those engine operating points and all? So I am going to explain in subsequent slides. So we have designed now a variable ignition timing, variable valve timing, then high thermal isolated materials, reducing the thermal losses, and so on. Introduction of CRDA systems, common rail design injection, and so on. Then properly matching of transmission. Why the present vehicles are having 5 speed, 6 speed, 7 speed, rather few vehicles are having 8 speeds and all. So we have optimized the engine operating points. So what are those engine operating points? You will see in next few slides. So properly matched transmission, this is one of the technology. But even after all those things, we cannot avoid burning of fuel, right? So we have no alternative for going towards a alternate drivetrains, means use of HEVs, electric vehicles, and ultimately the fuel cell hybrid electric vehicles. It will be a ultimate future. So IC engine versus EV. Conventional IC engines provides good performance, long operating range, which is one of the drawback of electric vehicles. We are not having that much of range. If you want to increase the range, then we have to use higher size batteries. So cost again is a factor. Then mismatch of engine operating points, which will give us a bad fuel economy. So we will see these points in subsequent slides. One of the thing again, dissipation of vehicles kinetic energy during braking. So in case of electric vehicles or hybrid electric vehicles, we are having a regeneration braking capability. Means kinetic energy of vehicles whenever we are pressing a brake or whenever we are going down the hill. So that kinetic energy of the vehicles converted back into electric energy. So it is known as a regeneration braking. So there will be less loss or less dissipation of heat, which is otherwise happen in IC engine vehicles. And lower efficiency of the transmissions. In case of electric vehicles, we may not require for going to multi-speed gearboxes, which is a mandatory thing in case of IC engine vehicles. So I have explained you engine operating points. So what do you mean by those? Okay, so engine power output. So it is actually known as a typical ISO-SFC curve or brake specific fuel consumption curve. Okay, so engine power output, or you can call it as a torque as well, because power and torque we can plot against a engine speed. So engine speed is a x-axis, y-axis is the engine power output. It is a power curve, and we are getting a maximum power at a particular RPM. I have explained you those things, and these circles are known as a onion diagram. This actually known as a onion diagram. What do you mean by this? It is the specific fuel consumption in gram per kilowatt hour. Means how much fuel my engine is taking for producing a particular power when it is operated at a particular engine RPM. So it is known as a gram per kilowatt hour. For example, if my engine is operated at this point, so BSFC is 700 gram per kilowatt hour. So the engine is consuming more fuel. Okay, so our target is to shift those engine operating points towards the best BSFC zone. Now, whenever I'm driving a vehicle, okay, so depending upon the gear ratio and depending upon the final drive ratio, we are forcing engine or forcing any power plant to provide a particular power and which is operated at a particular speed. Suppose it is an engine, and it is, suppose for example I am going with a 50 kilometer per hour speed. So engine is operated, for example, at certain 3000 rpm, and it is producing power output of say 50 kilowatt or 45 kilowatt, and at that portion my engine is consuming 500 grams of fuel for providing me that much of kilowatt power. So 500 gram per kilowatt hour will be the fuel consumption. So our target is to reduce these figures. So if you see here now the curve, this curve is when I'm driving a vehicle in a city. If you are driving a vehicle in a city, generally we are operating or we are driving the engine vehicle in first, second, max third or fourth gear. We are not going into fifth gear or sixth gear and so on. So at that time, engine is operated somewhere over here because our vehicle velocity is less, and which is directly proportional to the engine speed or power plant speed. So if we are operating most of the times over here, so this is known as the operating point of an engine. So why it is important to understand, I will show you in subsequent slides. So if you see here, maximum cluster you can get at 4400 or 500, okay, gram per kilowatt hour. So whenever we are driving our vehicle in a city, engine consumes more fuel. So that's the reason we are calling the in city we are getting a less mileage. Okay, it is actually a reason for that. And whenever we are driving our vehicle in a highway, so definitely we are going on a higher gears, fifth gear, sixth gear, seventh gear, right? So we are operating now, we are moving these operating points away from those lower engine RPM towards certain engine RPM where BSFC is less. Okay, so if you see here, whenever same vehicle, if you are driving on a highway, all those operating points from the lower engine RPM, lower torque region or lower power region have been shifted over here towards the best BSFC points. So whenever we are driving our vehicle on highways, we are getting the best fuel economy. So it is actually reason behind it. And as I told you, so typical brake specific fuel consumption curve will be like this. So at a particular RPM, we will be having a best fuel economy consumption, and at a lower RPM, again at a very high RPM, we will be having a worst BSFC. Means engine is consuming more fuel for producing a particular power. Any hybrid electric vehicles consisting of IC engine, then motor, transmission, batteries, power electronics, and other systems remain same: HVAC, chassis, braking, suspension, etc., etc. So those only the addition here is a motor, battery, but here the controllers are a very critical thing to design. So we'll see all those things. So it is actually, these are different components. DC-DC converter, again thermal system design is very important over here, because if you know, we have to cool our IC engine, as similar to that we have to cool DC-DC converter, motor, battery, because lot of heat is generated. So lithium ions are very sensitive to heat. Whenever heat is generated beyond certain limit, it will give less efficiency. Battery will be having very worst efficiency. So efficient design of thermal system is very important over here. Now we will see few more basics over here. So conceptual illustration of hybrid electric vehicle. Okay, so engine, energy source one, energy converter one, that is IC engine and the converter. Source means diesel, and the IC engine. Here battery and the motor. Okay, so one powertrain one and powertrain two. One powertrain must be unidirectional and one powertrain must be bidirectional. So why it is so, we will see in subsequent discussion. And then summation of the power and the load. Here load means what? Tractive effort requirement. I have explained to you in earlier slide. So what exactly the tractive effort is? Rolling resistance plus aerodynamic plus gradient resistance. So load required for at the wheels, and we have to size the powertrain in such a way that the vehicle can negotiate that much of load. Otherwise vehicle will not move if power provided by the power plants is less than this load. So 9 different modes are available in case of hybrid electric vehicles. Powertrain 1 alone delivers the powertrain to the load. Means, for example, powertrain 1 is an engine and powertrain 2 is an electric motor. You can say battery and the electric motor. So engine alone propelling mode. Second is pure electric mode. Only powertrain 2 delivers the power to wheel. Then both IC engine and electric motor supplies power to wheels. So we are having a summation over here. How to do that summation we will see later on. So that is a hybrid traction mode. Then regeneration mode, I have already explained you. So this is actually a regeneration. Whenever I am pressing a brake of or we are moving in a vehicle which is going down the hill, kinetic energy gets converted into electrical energy. So from the load, we are forcing motor to act as a generator, and it charges the battery. Okay, so it is actually a reverse power flow takes place. So that is the reason one power plant must be a bidirectional. Engine is not having that capability. So you all are aware of it. So motor can act as a motor means in a forward direction and generator in a reverse direction. So that is the reason battery and electric motor acts as a bidirectional. So for providing or for facilitating any regeneration braking, one power plant must be a bidirectional one. Then engine charges the battery while vehicle is at standstill, coasting, etc. Both regeneration braking and IC engine charges the battery. Engine propels the vehicle and charges the battery simultaneously. Engine charges the battery and battery propels the vehicle, and power flow into batteries from both engine and heat engine through the vehicle mass. So there are different modes available with the help of a hybridization, and we have to develop a control strategy effectively so that we can make optimal use of both the power plants, because both the power plants and both the power sources are available with you. Then power decomposition. So whenever we are driving a vehicle, so we are having a dynamic load. So load is not a constant. So we are having a differential requirement of the load depending upon the road traffic, or depending upon depending upon where you are driving the vehicle in city, on highways, and so on. So IC engines and fuel cells are having best efficiency whenever they are driving, whenever we are taking a average power out of them, and they are having a worst efficiency whenever we are pulling a dynamic power out of them. So here both the power plants are available with us on board. So we can make use of IC engines and fuel cell for taking a average power, and whatever the dynamic power left for providing that for satisfying the load requirement, we can take it from the batteries and the motor. So this is how decomposition of the power we have to do. Then again, depending upon placement or topology, here we are having different kinds of hybrid architectures. So series hybrid architecture, full parallel, series parallel, and complex. So we are going to see in detail full parallel hybrid electric vehicles. But I will explain you here all those things. So fuel, in case of series hybrid electric vehicles, IC engine is not directly connected to the wheels. So if you see here, the IC engine is there, but motor drives the wheel. So fuel tank provides power fuel to IC engine. IC engine is coupled with a generator, and then the DC power available from the both battery and that whatever generated from the generator is coupled over here in the power converter, which acts as an electric coupler, and it provides the power to the motor. Whether it is a AC motor, generally nowadays we are using a AC motor, then again we have to provide over AC to DC, DC to AC converter, and then the electric motor supplies power to transmission, finally to the wheels. So IC engine is not directly connected to the wheels. In case of full parallel hybrid electric vehicles, both IC engine and the motor are coupled together with the help of a mechanical coupler. So instead of an electric coupler over here, so we are having a mechanical coupler, and both the power plants are connected to the wheels. Okay, so either IC engine drives the vehicle, either motor drives the vehicle, or both the power plants drives the vehicle. So both of these are having some pros and cons. So we will see what are those in subsequent slides. And for that series parallel hybrid electric vehicle and the complex hybrid electric vehicles, some people are using. For example, Toyota Prius. So you might be knowing Toyota Prius is one of the very successful hybrid electric vehicle developed by Toyota. So those are using a complex kind of hybrid electric vehicle. So I'm not going to touch all those things over here. So we will see full parallel hybrid electric vehicle in detail. Before that, I will just touch to series hybrid electric vehicles. As I explained in earlier slides, IC engine is not directly coupled to the wheel. Okay, so IC engine is connected to the generator. So that is the reason you can apply or you can operate the IC engine at whatever speed you want, because as I explained you earlier, speed of the vehicle is directly proportional to the speed of power plant, either it is a motor or either it is a IC engine. And if we are decoupling IC engine over here, so we are having that freedom to operate the IC engine in its best BSFC zone. So that freedom we can take in case of series hybrid electric vehicles. So IC engine is connected to the generator, which is again connected to the rectifier, because here AC signal have been generated and we have to club with the DC power supplied by the battery. So rectifier plays that role, and here DC converts AC into DC. So DC and DC power addition takes place, which is known as a power coupler, and then it is connected to the motor controller. So depending upon type of motor used, again we have to convert that. Okay, so that DC again converted into AC and fed to the motor, which gives drive to the transmission, and finally vehicle is driven. So pure electric traction, pure engine traction, hybrid traction, regeneration, battery charging, all those modes are possible over here. So controller development, as I told you earlier, vehicle controller is a brain of any hybrid electric vehicle system. So what it does, it takes signal from the wheel. Means, as I told you earlier, how much traction required. We take that from the wheels. Then what is how much fuel we need to inject inside the engine. So that have been taken. That control have been taken from the engine controller, and how much SOC is left inside the battery, state of charge. So that signal have been taken from the PPS, peak power source. And all those things vehicle controller takes into calculations. Then it sees what exactly the operators demand, whether you are pressing acceleration or you are pressing a brake. Okay, so that all those things vehicle controller computes, and depending upon that, it provides a signal to motor controller and to the engine controller for providing particular power to the wheels. So that is the reason vehicle controller design is actually a very critical in task in case of hybrid electric vehicles. So series hybrid electric vehicles advantages. It is a very simple configuration, no mechanical connection between engine with a driven wheels. So engine is small. You can operate engine at any speed band you want whenever there is a best BSFC. So that narrow region is there where efficiency and BSFC is less. Efficiency is more and BSFC is less. So you can operate the engine in that region. Motor here acts as a main prime mover. It eliminates use of multi-speed gearbox because we have not connected engine directly to the wheels. So no need of having multi-speed gearboxes. Two separate motors in the wheels can be possible. Here battery pack is more powerful. Control strategy is very simple. Start, stop, go type of vehicles can be uses this technology. Means buses, trucks in urban vehicles are having this series hybrid electric vehicle technology. Some disadvantages are there. Energy conversion takes place twice, mechanical to electrical in generator, and again electrical to mechanical in traction motor. So here to multiply the total power available at wheels with the help of these two efficiencies. So ultimately efficiency will be less. Then generators generally having inefficient, generally known as an inefficient power plant. So compared to traction motor, but here ultimately, as I told you, we have to multiply that efficiency to the motor efficiency. So final efficiency will be less. Then generator adds weight, and traction motor only acts as a prime mover over here because IC engine is not directly connected to the wheels. So battery pack is more powerful. So larger sized batteries we have to use. So this is up to this is it up to the series hybrid electric vehicles are concerned. So I think you have now understood what exactly the series hybrid electric vehicles are. So now we will see full parallel hybrid electric vehicles. We have seen in earlier slides, IC engine and electric motor both are coupled with the help of mechanical coupler, and then finally to the wheels via transmission. So we are having a mechanical coupler over here, which couples the mechanical power outputs coming from the both the power plants. So pure traction, pure engine traction, motor traction, hybrid traction, regeneration, all those modes are again possible over here. Whenever you can see this backward arrow, it is a regeneration. So all those things are possible in case of full parallel hybrid electric vehicles as well. So this typical characteristic curves already we have seen. So as we have seen, engine will not provide a maximum traction or maximum torque at a less vehicle velocities or less engine RPMs, but motor can does, right? So this is the reason we have to introduce here a multi-speed gearbox. So it is actually a ideal traction hyperbola. So few basics about why multi-speed gearbox is required. So imagine maximum power provided by the engine. So it is a maximum power provided by the engine. And if you are having a particular power plant, now forget about motor and the engine. I am having a particular power plant which can provide me a maximum power at all the speed range or all the velocities of the vehicle. In that case, you will be having the curve of a particular power plant like this. It is known as a traction hyperbola by the capacity or design of tires, because whatever power you are providing for propelling the vehicle, tires are also should withstand that much of force, which is known as a adhesion limit. Okay, so now consider IC engine is used. Okay, so here we are using a IC engine which is providing us a maximum power at a particular engine RPM. Okay, this is maximum power at a particular engine RPM. So amongst all this energy which is available in a shaded region, with the help of engine, we can harness only this much of energy. So what about other energy? So here we will be having a very less amount of energy available at the wheels if we are not using a gearbox. And with the help of IC engine, means IC engine and a single speed gearbox, you cannot provide a maximum velocity, you cannot satisfy the requirement of maximum gradability and so on. Why? Because IC engine will provide this much of power with the help of single speed gearbox. In order to come out of this situation, we have to use a multi-speed gearbox. So amount of energy which is available at the power plant. So what we are doing by this multi-speed gearbox is simply multiplying that speed and torque characteristic of a IC engine in such a way that the maximum gradability torque required at a maximum gradability can be achieved, then power required for propelling the vehicle at maximum speeds can be achieved, and so on. So that is the reason multi-speed gearboxes are required whenever we are using a IC engine. And it is not the case in case of an electric motor, because electric motors characteristic curve itself, it is like that. If I have told you, it is a ideal curve available by the power plant. So if you go and see here torque curve or speed curve of a electric motor, it will suffice all my requirements. It will provide us a maximum torque even at a low vehicle RPM. It will provide us a maximum power at a very high speed, and so on. So that is the reason we will be not requiring a multi-speed gearbox in case of electric vehicles. And in case of a hybrid electric vehicles, as engine is connected directly to the wheels, we have to go with the multi-speed gearboxes. So this is one of the disadvantage actually over here. So advantages of full parallel hybrid electric vehicles is what? Efficiency is more. So we are not having generator as in case of a series hybrid electric vehicles. So engine is directly connected to the wheels and motor is also connected to the wheels. The energy loss is less, as we have seen in a series hybrid electric vehicles. Powertrain here is a compact because no generator, and traction motor is of smaller size. So batteries are also smaller sized. But as I told you, we have to introduce a multi-speed gearbox over here, so it is having its own disadvantages. So we have to go for a automated manual transmission or automatic transmission, CVT, DCT kind of architecture. And here control strategy development is very difficult task, because we have to control powers coming from the engine and power coming from the motor simultaneously. So controller development is a very critical task over here. So what exactly a coupling is? So in earlier slide we have seen, if I go back to this slide over here, so here summation, you have seen this summation. So we are coupling powers from both the powertrains, but how to couple it? So can we do simple addition or multiplication? So we will see that now. So there are two different aspects or two different modes. From that we can couple the powers of these two power plants. First is a torque coupling and second is a speed coupling. In case of torque coupling, engine and motor torque can be independently controlled, and in case of speed coupling, both power plants speed can be independently controlled. So here we will see what exactly I am going to tell you. So see the now free body diagram of any hybrid electric vehicle: IC engine, then torque coupling, and the electric motor. As I told you earlier, one power plant must be having a bidirectional power flow, and engine is not having that capability. Bidirectional means we can use the motor as a generator for the regeneration. So torque and speed of an engine and the motor, and finally torque and speed at the wheels. So torque and speed at the wheels means power available at the wheels. Power is equal to T omega. So power available at the wheels is equal to power of the engine plus power of the motor. But here, as I told you earlier, we can vary the torques independently for both the power plants. So here we have to take a particular constant by dividing by speed of a wheels. Okay, so K1 is equal to omega 1 by omega 3, K2 is equal to omega 2 by omega 3. So here we can vary T1 and T2 independently for getting appropriate power or torque at the wheels. So how to do that? So there are again different kinds of configurations. So we will see the line diagrams of those. Engine connected with one of the transmission, motor is connected to another transmission, couple that both at the end with the help of a torque coupling. So this may be a planetary kind of system, and finally the output taken at the wheels. So this transmission can be multi-speed, which is connected to engine. Transmission 2 can also be multi-speed, but earlier we have seen whenever we are having a motor, no need of having multi-speed transmission. So transmission coupled to the engine can be a multi-speed transmission, 4, 5, 6 speed, and transmission coupled to the motor may be single or maximum 2-speed configuration, and we can take output at the wheels. So it is known as a two-shaft configuration. We are having two different transmissions connected to two output shafts of the power plants, two-shaft torque coupling. Then here, either you can couple the torque before the transmission. Okay, earlier we have transmission. So rather than using two different transmissions, we can couple the torque with the help of single transmission. So torque coupling over here we can use in between the power plants and the transmissions. So these configurations allows electric motor and engine to reach their maximum speeds at the same time. This configuration is suitable when relatively small engine and electric motors are used. Okay, so this might be its drawbacks. So it is also a two-shaft configuration, but single transmission. It is a torque coupling again I'm talking about. Then single shaft pre-transmission. Okay, so single shaft test before the transmission. So it is known as a pre-transmission. Engine is coupled to motor, motor coupled to transmission, and then finally drive is given to the wheels. So here torque of both engine and torque is modified with the help of transmission, because transmission is after the power plants. However, torques of engine and motor are required to have the same speed range, because here engine and the motor are connected with the help of a single shaft. So you can't operate both those power plants by at a different speeds, otherwise every system will break. This configuration is useful for again a small motor referred to as a mild hybrid electric vehicles. We have earlier seen 10 to 20% degree of hybridization. In those kinds of vehicles, this configuration is used. So Maruti Ciaz, is it actually a mild hybrid electric vehicle? So those kinds of vehicle uses this single shaft pre-transmission. Then single shaft post transmission, motor is kept at after the transmission, so it is known as a post transmission. Again single shaft, because we are having a drive on a single shaft, engine, transmission, then motor. So it is a torque coupling with a single shaft post transmission, and we can have freedom of providing drive at with the help of IC engine and with the help of motor to both the axles. Means one axle will be driven conventionally with the help of IC engine, one axle will be driven with the help of motor, and efficient controller will be developed so that there will be a synchronization between the power coming out from the both the power plants. Now till point we have seen what exactly is a torque coupling. Now we will see what exactly is a speed coupling. So earlier we have varied the torques separately. So here equation will be the same, because it is a energy conservation equation. So here we are changing the speeds of both the power plants separately, independently. So it is actually a complex architecture. So as I told you earlier, Toyota Prius. So Toyota Prius is using this kind of configuration where we have to use a planetary drive. So engine, transmission, and motor. So if we see, we will see how those different modes have been achieved. So we are having a planetary set over here. So sun gear, then planet gears, then ring gear, okay, and planet carrier, which is having a drive to wheels. So lock 1 is to lock sun gear and lock 2 is to lock a ring gear. So hybrid traction mode. So when lock 1 and lock 2 both are released, so both the power plants provides power to the wheels, so we can get a hybrid traction. Engine alone traction, when lock 2 locks the ring gear. Okay, so lock 2 locks the ring gear. Why we are locking the ring gear? Because ring gear have been given a drive from the motor. So we are locking a drive which is provided with the help of an electric motor. So lock 2 have been locked to the ring gears with a vehicle frame, and lock 1 is released. So conventional electric motor we can get. And when we do other way around, lock the sun gear so that no power output from the engine, and release the lock 2, we can get a electric drive. And then finally regeneration braking, when lock 1, lock 2 are released, and the battery charging mode. So different kinds of mode here again are possible, but here if you see, designing and manufacturing of these kinds of transmissions or these types of hybrid electric vehicle layout is very costly, as I explained to you earlier. So Toyota Prius, it is very costly architecture, so that entire cost of vehicle increases. Then again, this slide we have seen for in series hybrid electric vehicles. So still it remains the same over here. So vehicle controller is a brain. It sees the situation, actually accordingly provides the signals to engine controller or to the motor controller, so that both the power plants can be efficiently used. Now, a few strategies I will explain you over here. So actually, I'm doing some advanced research in my PhD work in these different strategies, but those I have not included over here. So very basic strategy I will explain to you. So power versus speed. So forget about whether whatever is the power plant. So here we are considering the vehicle speed. This is earlier we have seen power characteristic of a IC engine, power characteristic curve of an electric motor, and we combined both, so we are having certain power characteristic curve for a hybrid mode. Okay, so consider the requirement of a load is over here, somewhere here at the point B. So this point is below this maximum power curve of a IC engine. So only the IC engine can be capable of providing a power to wheels, but at the same time, controller sees what exactly the state of charge of battery is. Suppose my power requirement is at point B, but my state of charge of battery is only 30% or 40%. So vehicle controller decides, yes, we have to charge the battery now. So what it does, it operates the IC engine at this power, because this is the maximum power available by the IC engine. Even though my load power requirement is less than this, but my SOC is less. So what exactly vehicle control unit does, it operates the IC engine in this region. It allows more fuel to go and burn, and only this much of power is only provided to the wheels, but remaining power will be provided for charging the battery. So this is how efficiently it operates the power plant or IC engine. Now consider point A. Okay, so my power requirement at the wheel is at A. Neither power IC engine alone nor motor alone provides this much of power. Again, the vehicle control unit comes into picture. It does internal calculations. It operates the engine over here at its full load characteristic curve, because engine can provide me only this much of power, and the remaining delta will be taken from the motor. So this is how combined mode comes into picture. Both IC engine and the electric motor provides a power, so that the power requirement at the wheel will be satisfied. Now you will ask me, suppose power requirement is somewhere over here, what to do? Here in hybrid mode also, my power plants are not capable of providing that much of power. So we have to go and do the sizing again. So we have to go on increasing size of the motor. We have to do the basic calculations for increasing power characteristic of a motor, so that in all the scenarios, this power requirement at the wheels should lie below this maximum power available in a hybrid mode. Okay, other way around, now we will see. So what exactly is this? So earlier I have told you, so regeneration braking, kinetic energy converted into electric energy. In that case, this power curve exactly we have to take as a mirror. Whenever motor acts as a generator, that curves become a mirror image. So this is now the braking power available by the power plant. Now suppose my braking power over here is point number C. So what I will do, I will simply remove my foot from the accelerator pedal. So vehicular control again picks, yes, this much of amount of braking vehicle is required for its reducing its speed. So motor acts as a generator, and regeneration braking comes into picture. And whenever my requirement of the brake is over here, which is lying outside this maximum power in a generator mode, motor is providing. In that case, only regeneration braking is not sufficient. So maximum regeneration will be this much, and remaining delta will be a conventional friction brakes. So in this case, less amount of energy is dissipated in the form of heat. Otherwise, we are not harnessing this much of energy in case of IC engine vehicles. So this is actually basics of a regeneration braking. Another simple strategy, engine on-off strategy. Whenever PPS SOC means peak power source, means battery's SOC is at extreme limit, just switch off the engine, operate the vehicle in an electric drive mode till its SOC reaches to its lower limit. Again, the vehicular control comes into picture. Yes, my SOC is now 20%. It starts the engine, then engine propels the vehicle as well as charges the battery, and this cycle goes on continue. So like that, there are different kinds of control strategies: fuzzy logic based control strategies, minimization consumption based strategies, even GPS based strategies. So these I have explained you only two basic strategies over here. Transmission design, I'm not going into those details in the interest of time. So there are different kinds of technologies are there: automatic transmission, dual clutch transmission, CVT, AMT, and so on. So here, full parallel hybrid electric vehicles are, as I explained you, very complex control strategy need to be developed over here. We have to go with a multi-speed gearbox. For that, we have to go with an automated transmission or AMT or DCT, like that. Few of the examples: Toyota Camry, Honda Insight, then Toyota Prius. So always I'm talking about you. This is the vehicle. So few of the you can see those vehicles on Indian road. So Toyota Camry, Prius are available over here as well. So case study. So here, before developing any model, so I have explained you earlier V approach. So you can't just go and size the components and directly place inside the real product. So we have to do some software in loop simulation, hardware in loop simulation, some test bench tests. We have to model some mathematical models in softwares like MATLAB, Simulink, and so on. Okay, so all those things we have to do at a simulation level. Then placement of the components, where to place battery, where to place a motor, how should be the integration of those, where to put a high voltage systems, that should not be near to exhaust of the vehicle because we are having exhaust as well because of ICE engines and so on. So this exactly this is how we have to optimize the placement of these different power plants. So battery, we can put the battery over here, entire floor. Teslas, these are having battery all over the floor. Types of batteries are also available. So this is known as a skateboard kind of chassis. Or if we are going with the conventional chassis, then we have to place the battery accordingly at appropriate positions. So this exercise we did at ARAI. So this is how we have to see where we are having a place for fitting all the electrification components, because engine will be there, because you are converting a hybrid electric, we are having a hybrid electric vehicle. The hybridization components at the same time, we have to take care of motor vehicles rules as well. So there are certain rules. So this must be the minimum ground clearance, and this should be the place where you can't put the batteries and so on. So there are so many regulations are there, so we have to take care of those as well. Depending upon the placement of this motor, there are again different kinds of architectures: P1, P2, P3, P4. Suppose the electric motor is placed between and gearbox, P1 kind of configuration. The same, if we are putting a battery, then it is known as the P3 configuration. At the differential or on the axles, if we are putting the battery, it is known as a P4 kind of architecture. Available. So Gamma Technology or AVL or Ricardo's or MATLAB Simulink. So on in those softwares, you can model entire physics of this vehicle, starting from engine, batteries, transmission, all the controllers. If you can see over here, hybrid controller, battery management system, electric motor controller, ECU, all those things we have to model over here first, and then in simulation environment, we have to check how much fuel economy benefit we are getting. So how you are going to do that? So for that, there are different cycles. For example, New European Driving Cycle, NEDC, then Indian Driving Cycle, IDC, MIDC, then US FTP cycle. Those are different standard cycles all the countries are using for doing the homologation. So see how ARAI is predicting mileage. I will show you later on. So here, vehicle will be driven at a particular speed, at a particular on a particular gear at a particular time. So it is actually a standard cycle. You can't change this. So we have to do a simulation, or we have to do a laboratory tests for these particular cycles for claiming the fuel economy or for determining the engine operating points. So as I told you earlier, efficient development of control strategies. So what exactly we are doing into it? So whatever the low velocity regions or low speed regions where we are operating our engine in a lower gear, first gear, second gear, or etc. So we have seen earlier, at that time engine will be operated at its worst BSFC region, engine operating points we have seen. So those portions will be transferred on the electric motor region. So definitely you are eliminating the fueling over here. So we can get a fuel economy benefit. Whenever there is a deceleration, we are taking a help of recuperation energy. So brake recuperation or regeneration braking. Whenever we are stopping on a signal, we can use the start-stop technology. Whenever we are having a sudden acceleration, whenever we are going on a ghat section or a very high hilly region, so here we can club powers of both IC engine and motor. This is how at different regions we are making effective use of power plants, and when by this way we are optimizing energy output from those power plants. So this is one of the experiment or project we did at ARAI. So MIDC means modified engine driving cycle. Whenever the IC engine is operated, these are engine operating points. I have already explained to you power torque curve versus engine RPM. And when we are negotiating that vehicle on a MIDC, that is modified engine driving cycle, or NEDC, whatever it may be the cycle. So something fuel economy benefit we are getting whenever I'm driving the vehicle in an IC engine mode. Now we have to do a optimization design of experiments with a 5 speed, with a 6 speed, with a 7 speeds, with a different kinds of motor configurations. For example, I am using, for example, say 50 kilowatt IC engine. So I can downsize the IC engine to 30 kilowatt, and remaining output I can take from the motor. Accordingly, I have to design a battery. So this is how design of experiments we have to do. And then we did the simulation for P3 kind of architecture, means electric motor at the end of gearbox. I have told you. So motor may be the PMSM, permanent magnet synchronous motor, or induction motor, whatever it may be. Then if you see over here, orange are the engine operating points with the help of pure IC engine, and black are the operating points with the help of hybrid mode. So if you ask me what about the remaining driving portion, so those operating points have been shifted to the motor operating region. So certain points will be totally eliminated. So we have completely cut down the fuel over there, those points. So we have seen what are those points, those low velocity points or idling points. All those points we have directly shifted those points on the electric mode region or regeneration. So whenever vehicle is decelerating, directly we are using make of use of regeneration braking. And this is how we did that experiment of changing that or increasing fuel economy from 30 kilometer per liter 20 kilometer liter to 30 kilometer per liter. If you see here, substantial increase in fuel economy benefit can be achieved by efficient development of control strategy and efficient or optimally using these power plants. Here you can see whenever there is a deceleration, we are charging the battery. Whenever we are having acceleration, we are taking battery power from the battery. So this is how we are maintaining SOC. Okay, so within a prescribed band. So these operating points we have already seen. So this is what actually I was talking about. So whenever I am having a deceleration, if you see your battery gets charged, this is because of regeneration. And whenever I am having an acceleration, battery will be consumed. So here if you see, combined mode will be there. So battery will be depleted. Whenever having a deceleration, battery will be charged, and so on. So I'm not going into those details, what exactly NEDC and all. You can refer any textbook or internet sites. So this is how actually we are claiming a mileage on a test bench at ARAI. So we are having a chassis dynamometer, rollers are there on which vehicle will be mounted, emissions will be taken out of its exhaust, and driver will drive the vehicle for that particular driving cycle. For example, NEDC, I have explained you earlier, it is having certain pattern. So driver sees in a big screen, and accordingly he operates the vehicle sitting inside this vehicle, and ultimately we are taking emissions out of it and how much fuel have been burned. So this is how we are claiming a mileage. So this is actually at a particular standard temperature and pressure STP, you can say, at a particular driving cycle. So that is the reason mileage claimed in a laboratory will never satisfy your requirement at the actual conditions, because actually your mileage is depending upon traffic conditions and driver's driving scenario. We did some intermittent experiment as well at ARAI for hybrid electric vehicles. So whatever values I have told you, 30 kilometer per liter we achieved after hybridization. So we did some experiment with can we really get it or not. So we seen that simulation results are actually meeting our expectations in actual experimentation as well. And then while this process, we have designed this entire 7-speed automated manual transmission. So this is actually AMT, induction motor is there. Motor is driving, adding its drive at the end of gearbox. So here will be the propeller shaft. here will be the IC engine. So it is known as a P3 kind of architecture with a full parallel hybrid electric configuration. So electric drive have been added at the end of gearbox. So till time we have seen the hybrid electric vehicles, series hybrid electric vehicle, its different architectures, then different topologies, then different kinds of experimentations, how we predict the mileage, how to develop a control strategy for getting a optimal output from this power plant. Okay, so now I will touch few aspects about fuel cell electric vehicles. So see, fuel cell is actually a niche market or niche area, but everybody is now coming into a big way in this region. So hydrogen economy, as I told you earlier, our prime minister have already from Red Fort on 15th of August this year, they have told we have to shift towards hydrogen. So how to utilize that hydrogen? There are two different ways. Either use hydrogen inside the IC engine, but still you cannot eliminate NOx emissions and all. So another way to use this hydrogen in the fuel cells. So main topic of my PhD actually is development of efficient control strategy for the fuel cell electric vehicles. So what are fuel cells? The fuel cell is an electrochemical device, okay, which converts chemical energy available inside the fuel directly into the electrical energy. So whenever we are talking about IC engine, whether it is a gasoline, diesel, CNG, whatever it may be, so what we are doing, we are burning the fuel, producing heat energy. Heat energy is utilized by the engine to convert a mechanical energy, and the generator is used for converting this mechanical energy into electrical energy. So there are different conversion steps, but fuel cell will eliminate all those and will provide electrical energy directly from the chemical energy. So that is the reason IC engines are having very less efficiency, maybe 35%, max to max 40% nowadays. But fuel cell will provide you a maximum efficiency, more than 55-65%. But it is the efficiency of power plant. Whenever you are talking about again the use of this fuel cell in the vehicle, efficiency slightly reduces because of efficiencies of other components. So here fuel cell uses a anode, cathode. Hydrogen is provided at the anode, oxygen is provided at the cathode. So we are having electrolyte in between. Then hydrogen gets converted into H plus ions, and electrons are released from the external circuit or moves from the external circuit towards the cathode. So whenever these electrons are migrating from the external circuit, we are capturing or harnessing them for converting or for storing those charge inside the battery. This is how we are generating electricity by providing hydrogen at a anode and oxygen at a cathode. And what happens over here at cathode? H plus ions comes here. We are providing oxygen, and electrons are coming from the external circuit. Finally, we are getting a water at the cathode, electricity in this process, and the heat energy. So this is actually a typical fuel cell cross section. So it is having a membrane electrode assembly, then certain carbon black paper, then platinum will be acts as a catalyst over here, certain gas diffusion layers, bipolar plates. Hydrogen and oxygen are provided through these bipolar plates. Gas diffusion layer is a porous layer. So through that, hydrogen is coming over here for on the catalyst for the reaction. Oxygen is coming over here at the cathode side, and ultimately I have told you water have been generated, and in this process with the help of single cell we are getting a 0.6 volt voltage. So different cells or number of cells we have to use in series and in parallel for getting a particular power output from the fuel cell. So it is having a zero emission. You can directly say if you are having a pure hydrogen or hydrogen generated from the electrolysis process, then in that case we can say it is a zero emission, zero pollution device. Very fast refueling. Here hydrogen can be refueled in a fraction of seconds as compared to charging the battery for hours and hours. Then long driving range it is giving, which is one of the drawback of electric vehicles. So there are different kinds of fuel cells, not only these two which you are seeing on the screen: solid oxide based fuel cell and polymer electrolyte based fuel cell. So it is, in short, it apart from that, there are several fuel cells: alkali fuel cell, molten carbonate fuel cell. So we are not using those for the automobile application. Even SOFCs are not used for automobile applications, but few people have still used this, or they are doing experimentation for using this SOFC in case of automobile application. But whatever vehicles available on the road now, so like a Toyota Prius, so Toyota Mirai is one of the vehicle which uses PEM, that is proton exchange membrane or polymer electrolyte membrane fuel cell as a power plant. So here in case of SOFC, we are using again a conventional fuel, CNG, LPG, LNG, diesel, whatever it may be. We are burning that fuel, we are generating a hydrogen, and that hydrogen will be provided to the fuel cell for further reactions for getting electricity. And in case of PEM, we are using a pure hydrogen, 99.99999, 5 times 9% pure hydrogen is required over here. And because here we are using platinum as a catalyst, and it is very sensitive for CO or CO2 emissions, CO2 emissions. So it gets degraded, and finally efficiency will reduce. So that is the reason we will be requiring a pure hydrogen, which is to be stored on board. So how? So like this. So any fuel cell vehicle is a hybrid electric vehicle. So it is having a fuel cell, it is having a DC-DC converter, traction motor. Again, whether it is a PMSM or induction motor doesn't mean. Then hydrogen storage tank, then battery. So here we have to store this hydrogen. And you might be knowing hydrogen is the lightest element, first element in the periodic table. So for getting a desired range, we have to store this hydrogen at very high pressure, 350 bar or 700 bar. For getting the 350. So storing this hydrogen at very high pressure is a very critical or very costly affair. So that is the reason this technology is very costly. Fuel cell vehicles are very costly. There are different systems: fuel cell stack, hydrogen storage system, as I told you, air supply system, because at cathode we have to provide a air. For that we have to use a compressor. Again, cooling system is very much essential. Then DC-DC converter, battery, whether it is a nickel metal hydride or lithium ion battery, motor, and the power control unit. Again, the vehicle control unit will be the brain of this system. So this is how you can summarize. Oxygen is provided at the cathode, hydrogen, electricity is generated, and we are fed to the motor, byproduct is water. So certain modeling aspects now, in the interest of time, I cannot go into those details, how to model that fuel cell in a simulation environment and all. You can do that on a MATLAB Simulink based softwares, then MIL and or HIL kind of systems we can do. Then there are different approaches: kinematic approach, quasi-static approach, and dynamic approach for modeling of the fuel cell system. Not only fuel cell electric vehicle, any kind of hybrid electric vehicle you can design with these different approaches. Generally, the quasi-static approach have been used. Okay, so it is giving you certain benefits because as compared to other two systems. Here we have to again develop an efficient controller, because fuel cell electric vehicle, again I told you, it is a hybrid electric vehicle. So for that electric vehicle controller, hybrid controller, fuel cell controller itself, what should be the hydrogen percentage you have to inject inside the fuel cell, how much of the oxygen we have to inject inside the fuel cell, what will be the amount of water generated out of this reaction, how to dissipate that water, then how should be the cooling system of this fuel cell, because in this reaction fuel cell gets heated because it generates a heat. So efficient cooling system have to be there. Then hydrogen, as I told you, has to be stored at a 350 bar, but at the entry of fuel cell we have to provide it at a 2 bar only. For that, different hydrogen pressure regulators and hydrogen pumps. At the cathode side we have to use compressors, humidifier, because if you are providing a very dry air, so the membrane inside it, so which is helping protons to pass, it will rupture. So for efficient transfer of protons, it should be hydrated. So for that reason, the humidifier is in used. So whatever accessories you can see over here, apart from fuel cell, it is known as a balance of plant. So this is actually a typical characteristic of a curve of a fuel cell. Now we have seen this curve for an IC engine, we have seen this for a motor. Now the curve for the fuel cell, current density versus voltage, and there this is how it drops. Means, as I told you, current typical fuel cell will provide us a 0.6 volt voltage. So there are different losses. So activation region means initially whenever you are pressing the accelerator pedal, immediately reaction will not take place. So hydrogen have to injected, oxygen have to be provided at the sites. So in that certain loss will be there. Then ohmic region, there will be certain loss because of the resistance of the system, and the mass transport loss means whenever we are having a chemical reaction, as I told you, water will be generated. So water will get flooded. So we have to remove this water time to time, otherwise it will destruct this chemical reaction. So when you subtract all those losses, finally you will be getting a 0.55 to 0.6 volt at the output. And this is how we have to do a bifurcation of the power. Here, as I explained you earlier, blue have this power I'll be taking from the motor, from the fuel cell, because fuel cell will be efficient when we are taking average power out of it, and whatever the load requirements, dynamic load requirements, can be captured with the help of batteries. And remaining, we can use even a supercapacitors or ultra capacitors. I'm not going into those details now. So there are different ways of producing hydrogen. So I'm just keeping these slides. Steam methane reformation is one of the aspects, and we have to store that hydrogen inside this tank. So storing this hydrogen in these tanks at a very high pressure is very costly affair. If you see here, storage efficiency is only 6%. Means for storing 6 kg of hydrogen, we will be requiring 100 kg of tank. Okay. So this is how the fueling stations in future will come. And if you see now why to choose fuel cell over EV, EVs are having certain drawbacks of driving range and all. So fuel cell will provide us a maximum range. For example, Toyota Mirai at 7 kg of hydrogen stored at 700 bar pressure, it will gives us approximately 650 to 700 kilometers of range. If you compare those compared to the range obtained from the electric vehicles, it is far better for this particular storing capacity. So there are certain challenges between those two, battery electric and fuel cell electric vehicles. So one is the range, but charging infrastructure is the challenge for the battery electric vehicles. Same challenge is there for fuel cell electric vehicles. We have to establish a charging hydrogen filling stations, but only benefit is that you can fill this 7 kg of hydrogen at 700 bar within fraction of seconds, or I can say minutes. Moment to fuel cell electric vehicles, it is very costly technology. So we are getting a very long range is the plus point of this fuel cell electric vehicles. So there are few fuel cell electric vehicles apart from Toyota Mirai, that is Honda Clarity, Hyundai Tucson, and so on. So future trends of transportation, definitely the hybrid electric vehicles, and ultimately fuel cell electric vehicle will be the future. And apart from that, we have to harness, or we have to generate that hydrogen with the help of wind energy, solar energy, geothermal plants, and so on. Because otherwise, if you are producing the hydrogen with the help of steam methane reformation, you are again creating a pollution somewhere, not maybe at the end use, but we are producing pollution somewhere. So for having a zero pollution devices or power plants, we have to harness this renewable resources. So future trend, definitely you might be knowing India REVA. Actually, it is 1994 REVA have been launched. After that, so many National Electric Mobility Mission Plan have been unveiled in 2013. Then FAME policy came in 2015. FAME 1 was there. Now we are in FAME 2. It will last till 2022. Government have given certain incentives for different aspects. For example, demand incentive, charging incentive, administration, combined expansion, and so on. Even public awareness, even awareness inside the academia, and also on. So all those things, government is giving a big push for this FAME. Again, there are different depending upon the battery kilowatt hour rating. So government will be giving certain incentives. For example, if you see here, so battery kilowatt hour is 2 kilowatt hour. So for that particular vehicle, will be getting a 20,000 incentive or so on. So the government have allocated certain funds, maybe 10,000 crores of funds have been allocated for different activities for different segments of the vehicles. So definitely we are not seeing this right now in India, but in future definitely we are going to see this public charging stations. Nowadays, even the Ather Energy two-wheeler manufacturers, they are providing their charging station inside the apartments as well, whenever you are taking their two-wheelers. So we are going to see all those things in future. So key initiatives, introduction of this e-mobility governance, then development of e-mobility infrastructure, public exposure to the e-mobility, creating a strong e-mobility and R&D community. So all those things we have to see, and development of ultimately the business collaboration. Ultimately, fuel cell electric vehicle will be the future. Why? I have already explained those its pros and cons we are having, but still fuel cell will be the future. It will be providing a large range when we are producing and in true sense it is a zero emission power plant. All those figures I will not go into details. Is really EVs are zero emission? Answer is definitely no, because you are burning coal somewhere and taking electricity. But definitely when you compare well to wheel efficiency, well to wheel means from the power plant to the wheels. Okay, so that efficiency is definitely more as compared to ICE engine based vehicles. But fuel cell electric vehicles in true sense will be the zero emission power plants when we are producing a hydrogen through the electrolysis process. In electrolysis as well, we have to generate that electricity with the help of solar power and wind. So here government, academia, then vendors, OEMs like Tata Motors, Mahindra, all those big names and university, we have to work together for efficient development of this e-mobility and R&D community. So I'm thankful for you for your patience, and that's what I wanted to communicate to you. So if you are having any doubts, you can ask me now, or these are my contact details. You can mail me your doubts. I will definitely answer to you. Thank you all.
Hi, good evening, Rakesh sir. This
Hi.
is Pankaj Varde from Chemical Department. So
Yeah.
before we end up with the session, we would like to take questions from the audience. So I have already asked participant to post their questions, and I have questions with me. So let us
Okay.
start with our first question. That is, it is asked by Mr. Chetan sir, Mr. Chetan Pawar, and it says, what reliability issues might hybrid electrical vehicle will have? So, what do you say, Rakesh sir?
Okay, so reliability issue. See, so here we are having both the power plants on board. So IC engine and the electric motor, and obviously the batteries are there. So reliability issue. So depending upon how you are having your charging cycle, means charging cycle means what? Whenever you are charging your electric vehicle on from the grid. So if you see electric vehicles are coming with two types of charging options, fast charging or a slow charging. Okay, so fast charging definitely life of this battery slightly reduces compared to the slow charging way. So similarly here, so suppose how efficiently you are developing the control strategy. As I again I'm telling, if you are charging the batteries continuously, okay, while driving the vehicle, means we are taking engine power continuously for charging the battery, and without letting its SOC to go at a particular brand. Means for example, I am allowing engine to come into picture again whenever says SOC of the battery reaches to 50% rather than again allowing it to deplete to 40%. So in that case, life of the battery will definitely going to reduce. So definitely it will be having certain reliability issues. And whenever we are asking that electric mode to come into picture whenever vehicle is at a lower RPM or lower kilometer per hour speed, so in that case efficiency of those batteries and the motors will be obviously less, because as I explained you BSFC curve, batteries and motors are also do having their efficiency curves. So unfortunately I could not show those curves to you. So we have to operate those power plants or power carriers in particular region. At that portion only we are getting maximum efficiency out of it. So all those things, reliability related issues, performance related issues, we will be getting out of it if we are not having a optimal control strategy to play into picture.
Okay. Thank you, sir. We have one more question. It is from Mr. Suhas Bhalke, and he says, can we use combination of regenerative and drum braking for different pedal distance travel?
So that's what I have actually shown in one of the slide. So
Yes,
definitely drum or disc brakes will be there. You cannot avoid those things. Okay. So
yes,
otherwise you will be at risk. But suppose see, regenerative braking also you have to have separate controller. For example, suppose I'm driving my vehicle on a road and something comes immediately in front of me. I'm not allowing regenerating braking to come into picture. I will be braking. I will be pressing the brake pedal immediately. So rate of pressing of brake pedal will be very fast. In that case, regeneration will not come into picture. Your conventional braking only will act in that portion. Whenever there we are having nothing in front of us, and whenever we are driving the vehicle in the down the hill, so we are not pressing brake at a very panically. So in that portion only regeneration braking will come into picture. So braking system is a combination of regeneration plus mechanical. You are not having any other way to avoid the mechanical braking, so the mechanical braking have to be there. So that's the reason I have told you, whenever the requirement of brake power is more than that of provided by the battery in its regeneration mode, at that portion, that delta will be provided by mechanical braking only. Whether it is a disc brake, whether it is a drum brake, it doesn't matter.
Okay. Thank you, Rakesh sir. And I guess all other questions are really related to these two questions. So this because I am from chemical engineering background, I am interested in the last part that you have spoke about fuel cell vehicles and hydrogen vehicles, hydrogen fuel cell vehicles. So basically, my question is, I know that storing a hydrogen, it's really a big trouble right now. So, is there any new research have came in recent studies or something like that to avoid or to improve this storage problem of hydrogen? And I know, and one more thing, will it be, matlab, in coming future? What do you think? Which technology will be pocket friendly for middle class people like us? So, what is your view on that?
First, answer to your first question. So there are different now methods or technologies for storing the hydrogen. So hydrogen. So BMW, they have done one experiment with a liquid hydrogen. So liquid hydrogen means what? Hydrogen they have stored at a cryogenic temperature, minus 250 or
Yes.
minus 280 something, that cryogenic temperature is there. So for that they stored, but storing the hydrogen at cryogenic temperature is having other issues, because suppose there is certain leakage, then there will be a boil of losses. So you can't get
Yes.
rid of it. So yes, they have done this exercise with a automobile, but it is not yet successful. So at this moment, storing the hydrogen at a very high pressure. See why they have stored at a very high pressure, because our requirement is to get a maximum range. In India scenario, suppose we will be requiring only 120 or 200 kilometer range. We need not even require to store hydrogen at 350 bar. We can store at a 180 bar, 200 bar, and so on. Secondly, there are different methods to store the hydrogen. Chemical hydrides are there, metal hydrides are there. As I told you, cryogenic storage, gaseous storage, so many methods are there, but they are found to be not as efficient as storing the hydrogen at a gaseous state. So that's the reason only the whatever technology till date have been evolved, it is with a gaseous hydrogen. Definitely, the research and some demo vehicles are there which are working on a cryogenic hydrogen. Answer to your second question, definitely we are going towards electrification. We are going towards very high-end technology like fuel cell electric vehicles and on. But at this moment, this technology is costly, as you know. So definitely for all the incoming future up to 2040, 2050, whatever it may be, all those technologies will coexist. IC engines will never die, never going to die. For those will be there for heavy commercial vehicles like trucks, buses. Even in case of a marines, definitely there will be IC engines will be there. Fuel cell, yes, some of the researchers or some of the OEMs, they are working in a way to use this fuel cell or hydrogen technology for the buses in bus segments, because it will be very difficult to have this technology in all the passenger vehicles we are now running on the road. So it will take some time for getting its cost down, because battery, so many factors are there in case of fuel cell electric vehicles: cost of battery, cost of hydrogen, even cost of platinum. Platinum is one of the costliest metal, and we are using it as a
Yes.
catalyst. So that is the reason
Yes.
actually fuel cell electric vehicles are costly. But definitely the demand, if demand increases in future, and develop hydrogen is available at a cheaper rate, then in that case definitely cost is going to reduce. See, take an example of mobiles. 10-15 years ago, mobiles were very costly. Now everybody is having
Yes.
mobile in their pocket. Same thing is going to do or happen over here. So definitely all those technologies will be there. Cost is also definitely is going to reduce. Still we have to wait for it. It is a matter of volume, because once volume increases, one demand increases from the customers like us, it is cost is going to reduce. But all those technologies will coexist. CNG vehicles, gasoline vehicles, petrol, diesel, then electric vehicles, fuel cell, hybrid electric, all those technologies will coexist in different segments.
Yes, yes. Thank you. Again, a very small question from again my side. What do you think? Developing a new technology is bit harder, or like the transition from the older technology to newer technology? Because right now I can see uh, the petrol cars. Then we have developed for CNG cars, and now we are going towards the EVs. So the transition is like for middle class people or middle class person like me. I see this transition is very difficult. Matlab, when I see there are no charging stations for EVs, and again very less CNG stations also. So again, quickly, can you tell me what would be the difficult part? Because we have a very
See,
less time.
okay,
Yes.
as it is my personal opinion, I can say both those things are very difficult. Transition itself is difficult, and evolution of new technology, this will also difficult. You have correctly said example of CNG vehicles. CNG is not a new technology, so it is like existing from several years, but still it is not become so popular as compared to the petrol or diesel vehicles. So even though from transition from one fuel to the another fuel, see there are different challenges, there are different pros and cons as well with the different fuels. So that is the reason actually acceptance from the people and all, it is having difficult things. So transition is definitely a difficult, but evolution of new technology is also equally or maybe slightly more difficult than that. For example, fuel cell electric vehicles, it is very difficult to come on the Indian or any roads. As I told you, there are different challenges on all. So as my personal opinion, both will be very difficult, transition as well as the evolution of new technology. But still,
Okay.
evolution of these fuel cells are now universally accepted. As I told you, all the OEMs are working in a big way. If you have heard to Mr. Mukesh Ambani in last month or 2 months before, so he announced 75,000 crores will be invested for generation of hydrogen and shifting this conventional fuel economy onto the hydrogen economy. So if the person like him is coming in a big way, then definitely even the evolution of new technology will also not be a difficult thing. Same thing have been demonstrated by Elon Musk.
Okay. Okay. Thank you, Rakesh sir. That was really insightful. So before we end the session, I would like to propose a vote of thanks. Uh, I, I thank Mr. Rakesh sir for giving much insight about electric vehicles, about hybrid electric vehicles, and about fuel cell technologies and how they are coming. And I really thank you, Rakesh sir, for taking out your precious time out of your busy schedule and coming here and giving a precious knowledge. And it was really very insightful for me also, who is from not mechanical background. So that was also a very interesting thing for me. So I again thank you, Rakesh sir, from DYP IMR family and the organizers of FDP. I thank you, and I'll request participant to stay tuned. We are we'll be joining again with again next sessions, and I request you guys to please the links have given in your chat box. Please fill your feedback links and attend. Thank you very much.
Yes.
Thank you again,
Sir,
Rakesh
I
sir,
am
for
also,
giving your
yes,
appreciation.
sir, I am also thankful for to you, to Vandana ma'am, and to entire DY Patel College of Engineering family, and I also thankful for all the participants. Even though I cannot see who have participated, but I am thankful to all of them.
Thank you. Thank you, sir.
Yeah,
Have a
thank you,
good
sir. Same to you.
Good evening and greeting to all dignitaries. I am Sarika Satpute, working as Assistant Professor in Electrical Engineering section of Dr. D.Y. Patil Institute of Engineering Management and Research, Akurdi, Pune. Privileged to have a pleasant task of welcoming our today's guest speaker, Mr. Alok Pendre sir, who is sustainability enthusiast, Eton India Innovation Center for this today's second session, which is on post-life impact of electric vehicle on environment under 1 week FDP on electric mobility as a future. I welcome you, sir. I feel honored to introduce our today's guest, Mr. Alok sir, in brief. Sir is the Center of Sustainability Team, EIIC Eton, lead engineer. He has completed his mechanical engineering from the University of Pune and post-graduation diploma in sustainable environment and postgraduate diploma in sustainable environment management from SIES Institute of Environment Management, Nehru. Sir has 10 years of experience in various fields of sustainability such as GRI reporting, CDP, and DJSI reporting, science-based target initiative, supply chain sustainability, scope 3 calculation, and verification product labeling, packaging and plastic waste reduction, circular economy, life cycle assessment, design for environment and product compliance, and many more. Before Eton, Sir had worked in many renowned companies like Godrej, Whirlpool, Mahindra and Mahindra for delivering projects on different sustainability topics. He had also worked for Gabby Software for life cycle assessment and DFE and also have experience in external stakeholders reporting. Sir has also worked on supplier sustainability assessment and supporting team to improve their performance on sustainability aspects. Mr. Alok is looking after DFE deployment in all NPI and NTI projects for e-mobility sector. He also supports on various corporates projects like Scope 3 calculation, supply chain sustainability, and LCA projects from other sectors. With this brief introduction, I would like to request Sir to address the participant with his words of wisdom. Sir, please. Thank you, sir. Over to
Thank
you,
you.
sir.
Yeah, thank you. Hope I'm audible.
Yes, sir. You are
Yeah,
audible.
so thank you, Sarika ma'am, for introducing me, and I would like to thank everyone to give me this opportunity to present the end of life impact of the EV on the environment. So I'd like to share my screen first. Just let me know if you can see the screen. Hello. Okay. I hope you all can see my screen.
Sir, it's visible, sir.
Yes,
Yeah,
sir.
okay, okay. Thank you very much. So, as Sarika ma'am has already introduced, I am from the Eton India Innovation Center, where we have the Center for Sustainability as a team who works for the various sustainability projects on product improvement, product energy efficiency, and other aspects of sustainability. So, we work with all product groups within the Eton, with all the product group manufactured by the Eton, and we giving the proper sustainable solution to our customers. So for today's agenda, the topic of the today's is electric vehicle end of life. So from as being of sustainability teams, it is very much interesting topic for coming economy as a e-mobility. So definitely there are a lot of pros and cons are there. So we're going to discuss everything in today's presentation here. So today's agenda for the presentation is climate change and transport sector, life cycle thinking. So we have some case studies as well on this, EV architecture and key components and their compositions, recycling processes and its environmental impacts, need of a circular economy and alternate solutions, sustainability at Eton, and solutions that we have at Eton for the end of life issues, and finally the key takeaways. First topic is the climate change. So hope you know that a lot of in last 20 years the climate has we are talking about this topic called climate change, the temperature rise, and a lot of extreme events has been happened in last 20 years. The extreme weather events such as heat waves, droughts, floods, and biodiversity loss we can see this it increased, like it's twice than before the earlier decades. So these are happens because of the rise in temperature. If you can see the graph on the left side here, so the temperature, it is a temperature rise since 1980 till 2020. So almost we are almost reached 1 degree temperature rise in overall climate. So this is not only 1 degree climate is not if it is counting as very small, but this has very severe and serious effect on the climate, like other extreme events was happening. So why it is so climate change rise is happening? So this is because of the increased greenhouse gases emissions in the atmosphere, and how these greenhouse gases are coming in place. So due to the industrialization and lot of development and technologies, we have started using a lot of fuels, fossil fuels specifically, and these fossil fuels emits CO2, carbon dioxide, and carbon dioxide is one of the GHG gas which helps actually to keep our earth warmer for the sustaining uh, all the people, all the live living elements on the earth. So but increasing this CO2 in the atmosphere, it is getting the temperature rise with beyond its limits. So we can see that what is the earlier pre-industrial era in 1970s, the CO2 in the atmosphere around 278 ppm, but now in 2020 is rise around 417 ppm. So this is also lead to the again sea water level and the extreme weather events, lot of biodiversity. So as I told you that increasing CO2 emissions in the atmosphere causes the climate change. But what is the reason behind it? What are the other aspects which are responsible for increasing the climate change? There are a lot of like industrialization, there are a lot of technology development that we have done, and a lot of man-made reasons are there behind it. But what is the major reason is the climate transport sector. Transport sector is the one of the spine of any other any economy of the any nation in the world. We cannot completely eliminate the transport sector and solve this problem. So we need to see for the alternate solutions. If you can see here, the transport sector in the development country contributes around 30% of the CO2 emissions, and the other worldwide is 23% by 2050. And right now there are a lot of efforts are going on all around the world, like in COP21, in Paris Agreement by UNFCCC, your United Nations Federation of Climate Change and Control. So they have set a target. They have the initiatives, and it is climate change treaty signed by the 196 countries to limit the climate warming by 2%, and preferably 1.5% degree Celsius compared to pre-industrial levels. So we are again everybody is working on this particular target, and what is going to help us to reduce this emission is the e-mobility. Now the e-mobility is one of the biggest buzz around the world, which can help to reduce the carbon emissions. Right now, interesting fact about this: the climate change COP26 is already in progress, and it is going to start from 31st of October 2021. And I think there are again there's a science-based target has been taken to reduce the 2 degree and 1.5 degree. It is now going to take a further step, going to the net zero. So their appeal from the nations and the corporates that we can go beyond that whatever limit where we have, and we can reduce the carbon emissions completely from the environment by taking different initiatives. Okay, so the how the kind of electric vehicle going to help here in the climate change, and it will help to reduce the temperature, restrict the temperature 1.5 degree. If you can see that electric vehicles are powered by the electricity, and it is stored in the battery power packs we have. So considering only the use phase, like earlier the Rakesh sir had mentioned, on it, if you consider tailpipe emissions, from tank to wheel, there is no emissions are happening in an electric vehicle. If you can see in the graph on the left side, the aquamarine color here shown as the emissions happening from the from the IC engine vehicles for the average European car and most efficient car. If you take what this is the total emissions, and aquamarine is counting only the emissions happening at the tailpipe, and other emissions are which is inbound to the fuels are the from well to tank, what are the emissions are occurred for extracting, refining the fuels, that also counts, that also have some effect of the on the environment. That's shown in the red. And last one is the other manufacturing, whatever the energy been expended or the in the manufacturing the vehicle, it's counted here. So if you can see the emissions here in the for the normal ICNG vehicles is higher than the electric vehicle on the right side. The under right electric vehicle is shown at the different countries in the Europe. If you can see, interestingly, Norway has no red bar here. So why Norway has no red bar? So red bar here indicates as the emissions cost for the fuels which is been used for the driving the vehicle. So here the fuel is used as a petrol or gasoline or diesel, but here the fuel is used electricity. So electricity has its own impact, like extreme, that somewhere is a coal is burned, somewhere is the power hydro. So that coal also have some emissions, so that effect also counts here. But Norway has a electricity. Norway is run through the 100% renewable energy. So if we charge the electric vehicle in the Norway, so ideally it will not have any impact in the throughout use phase, other than only manufacturing part of it, and other manufacturing part of it, and lithium and battery part of it. So that is a beauty of it, electricity of the going forward. You are always like Rakesh also mentioned that going forward to reduce the emission, we should look forward for the countries like Norway to going 100% renewable energy. And definitely the AV help us reduce the emission by 1.5 degrees Celsius as well. There is one more regulations in India rather than the Paris Climate Agreement. Climate Agreement is the one of the agreement which is voluntary by the companies and the nations, and they are taken by themselves to reduce it. But there is a regulatory aspect of that's CAFE norm, that's corporate average fuel efficiency. Right now, for the corporate fuel efficiency target for the passengers vehicles in India is 130 grams per kilometer. But from coming days, from April 2021, 2022, the target is going to get more stricter, and fuel efficiency or the CO2 emissions coming from the vehicle had to be restricted by 113 grams per kilometer. So how this is going to be achieved by the companies which are manufacturing the cars in India? So they have to go to the either the hybrid or the electric kind of technology, or they have to go for the more efficient technologies or more efficient engine system, powertrain system. So this is the external factors are driving the electric vehicle movement. So okay, so going ahead, if we go going to the electric vehicle, can they solve the problem? Can we solve the problem of the entire sustainability or environment? But looking forward, going forward, there is a big problem is going to come ahead. What happened after the end of the life? What are going to happen to the electric vehicles after 10, 15 years of use, or the 1 lakh kilometer, 1 lakh 50,000 kilometers of use? It is going to get scrapped like this. So what is the future problem is that scrapping of the batteries, which is contains a lot of chemicals, lot of hazardous elements, and lot of precious elements as well, and other elements like power electronics and motors. So current scrapping policies, what we have, they are not adapted ELV or the electric vehicles in perspective. So that need to be changed. So thinking about the complete life cycle, we need to consider not only the manufacturing or the use phase of the electric vehicle, we need to consider the end of life vehicle phase of the vehicle as well. So going to the next agenda topic is the life cycle thinking. Is We need to consider the life cycle thinking. Life cycle thinking is the best way to understand the environmental impact. So whatever the impact happens, we should not consider only the manufacturing part of it or the raw material part of it. What is the impact? But there is a lot of impact happens at distribution phase, use phase, and the flip phase. So what happens at the raw material phase? So environmental impacts of extraction and the refinement and transport. Suppose the raw material which is required for battery manufacturing, it's coming from the South America, it's coming from China. The transportation of that also cost a lot of cost, as well as the emissions and environmental impact, and also the refinery. And going forward to the manufacturing, yes, manufacturing the batteries as well as manufacturing the entire vehicle cost energy. It will cause some pollutions as well. It has certain environmental impacts within the OEM manufacturing, as well as the manufacturing for the suppliers, the who supplies the parts for this electric vehicle. Then again the distribution. making the cars in the factory. We need to distribute to the entire country through the dealership channel or the sales channel. So again, to transporting those vehicles, that also till till it's been purchased by the actual consumer, there is some again energy losses or the emissions impact happens. And the next part is use phase. Use phase it's a in IC engine case, the use phase is whatever the energy efficiency, whatever the fuel used by the IC engine vehicle, that creates an impact. And in case of electric vehicle, the electricity impacts whatever the electricity consumed by the electric vehicle. So as I mentioned earlier, the pure electric vehicle may or may not be purely good for the environment. It's based on where it is coming from, what the energy is coming from. It is coming from the coal-based energy, then actually we are not completely reducing it, the CO2, and helping to reduce CO2 emissions. Maybe we are partly reducing it, but thinking about the complete cycle, we need to think about how we can reduce the use phase impact by using the more renewable energy as well. And last part is end of life, nothing but last but not the least, the end of life impact. So now we have talked about lot about what is happening the manufacturing and build capability of the electric vehicles and battery. But we need to think seriously about what is going to happen at the end of the life of the batteries and other EV parts. So there is also, it has also a lot of impacts for the recycling and getting the material back, and it will go to landfill, it will go for the incineration. So those are also impacts going to happen for the electric vehicle. So we will see the everything this end of life in detail in further slides. So, for explaining the end life cycle thinking, I have one good case study. I think it's a case study for the Ford Focus and Mitsubishi. This is done by the one of the UBC sustainability scholar, and for the better comparability, they have chosen the two vehicles which is of almost similar weight. One is Ford Focus of 1,355 kg, and another one is a Mitsubishi. It's 1,450 kg. And the parameters they are considered, they also mentioned, the it is considered that this Mitsubishi and the Ford Focus both are driven in Canada, where they have the CO2 emissions from the grid. It's 2.2 grams per CO2 per kilometer. And if it is gasoline power, then emissions are coming on 253 grams CO2 per kilometer. You can see the difference directly from here. The emissions difference in the if it is electric vehicle and gasoline powered vehicles, there is huge difference between the CO2 emissions in both cases. And the average life for the both vehicles also considered the same as 1,50,000 per kilometer. And you can see in the graph on the right side, the emissions which is happening on the which is in a brown color, a light brown color, and is 253 grams per 250 grams CO2 per kilometer. And compared to the electric vehicle is only 0.194 grams per kilometer. It's very less. I think I can say on the almost 1%, less than 1% of the entire emissions which is happening. But you can see in the contrary, the emissions which is happens because of the raw material, it's kind of 60% higher than the Ford Focus. So why it is so high? So there is again law of raw material impact in the Mitsubishi EV, or EV is coming from the batteries. Batteries are the key elements which causes the raw material impact. And 30 to 50% life cycle GHG impact also coming from the battery manufacturing and the raw material extraction which is required for the batteries. And the last stage is the decommissioning, the dismantling or the recycling of the electric vehicle or and the Ford Focus IC engine vehicles. The study has been seen that in complete recycling of the batteries, motors, and both vehicles, the 0.012 grams CO2 bin is emission is caused by the Ford Focus, and zero point 0.2 grams CO2 is caused by the Mitsubishi. Again, here the emissions for the recycling of the Ford Focus IC engine vehicle is lesser than the electric vehicle. So there are two aspects which is even if we say the electric vehicles are very good for the environment, but somewhere in the hidden, if you see the life cycle thinking, there are some facts that we need to definitely consider for the future. That there are some hidden areas that we need to address if we want to be truly sustainable. So, to explain this further, I would like to take you to the EV architecture and their key components. So, if you see the basic difference component what we have, I'm not going to go in that deep. the EV architecture. Just overall, what are the key components which is makes difference between IC engine and the battery electric vehicle. So the battery is the major part. The motors, majorly they are using. There are various batteries are available. Majorly, I'm talking about the pure electric pure electric driven cars, which is majorly use lithium and battery. There are some other battery also used for the hybrid electric vehicles. And the motors are permanent magnet motors are used for the better efficiency and better better energy transmission part. And the power electronics parts, again it's transmitting the power to the various devices, to the powertrain and to the wheels and other areas of where it is require electricity. So it is been done by the power electronic part. So the basic three components are distinctly different than IC engine vehicle. So going again deep into the battery composition, because this is going to discuss, we're going to discuss this in a detail. So I'm just going to go the overview. So again, the lithium-ion battery are the most preferred batteries in the EV, purely EV. This is because of the positive attributes it has, such as specific energy, specific power, durability, cost. It boosts energy, chargeability, and safety. Other type of battery may have a lot of drawbacks. So the majorly in pure electric vehicle, the lithium-ion batteries are used. And again, based on this cathode composition, again it has been divided into three, like NMC, NCA, and LFP. Again, the NMC and LCA have the good energy density, so it can give the larger range and better range for the electric vehicle. And but these are bit costly in nature because of the rare because of the elements like manganese and cobalt have been used in this. And LFP is a iron-based battery, which is very cheap. And we can see this battery where the range is not a prime criteria. Just there they use it, and the cost is a major criteria. There they are using the LFP as a cathode for the lithium-ion batteries. So in the cost perspective, the battery cells account for 60% of the weight of the battery and 40% by the casing, which is again the very essential part. The battery management system and thermal management system are very essential part of the battery. And if we say in the composition we have mentioned here on the left side tables, aluminum encasing, the aluminum stainless steel frames and casing are going on. The major takeaway from this slide is that high cost of the batteries due to critical materials like lithium, cobalt, and nickel. So this is we need to address this area. And next component is the electric motor. As I mentioned, that the most used motors in the electric vehicle is the permanent magnet motor. The permanent magnet motor are the reach high power densities and efficiency. That's why it has been widely used in most of the electric vehicles. And why and what is the problem with this? What is the issue with this? So motors maybe the can be recycled or can be recovered 100%, but there are elements being used right now, permanent magnet, which again contain 30% of rare earth elements like neodymium, dysprosium, and some minor amounts of uh, praseodymium and terbium. So these are the elements which are the very rare earth elements, and going in the future, this is controlled by the some countries, and it can be have the dictatorship cost modeling. So we can like we have the dictatorship for the fuels. It is driven by the mostly Gulf countries. So going ahead in future, the battery demands, the motor demands goes ahead, and if we require more and more permanent magnets, so this is going to be a problem for the electric motor as well. So in the R&D also going on worldwide to how we can develop the motors which cannot use any permanent magnets. The third part is the power electronics. Electronics, as majorly we in Eaton also we manufacture a lot of components of the power electronics. So I think earlier presentation Rakesh sir already talked about a lot about this power electronics. DC-AC converters converts the battery energy for the higher volume to the AC for the downstream motor, and inverter again converting the direct current from the battery, alternating current for operation of electric motor, DC-DC. Say it's again step down motor. So wherever the low voltage application, so it converts the voltage into the lower voltage and provides the various applications like mobile charger, AC, music system, and everything whatever required. And onboard charger, where the charging power we have at the AC at charging station. So that AC need to be converted into DC and provided to battery for the charging. So this onboard charger also be one of the key elements. And again, this is being the electronics part, it contains a lot of again precious elements like copper, gold, silver, lead, tungsten, and tin, all these elements. These elements are, you know, that a lot of it's again the recyclability of this elements is very key issue right now. There are no proper recycler who can recover, or the ethical recycle you can say, or safe recyclers are very rare. So it's again very big challenge to recover these metals from the recycling. And especially if it is goes to the countries like Africa or any other Asian countries, the e-waste recycling is the biggest social and environmental issues. The next, I'm going to go deep again for the processing of the batteries. Right now, if we consider recycling infrastructure in EU, there is already ELV directive already in place. Is a end of life vehicle directive. As per this directive, we there is a target is being given to the all the automobile manufacturers who's going to sell their vehicles in Europe, that they have to have reuse, recycle, and recover targets. Like 85% they have to be reuse and recycling of the components, and 98% reuse and recovery. So they have to achieve this target if they want to sell any vehicles in the European region. And this how this recycling happens as per this regulation. What are the regulations say talks about it? If first about depolluting. If you case take a case about e vehicle is going for the recycling as per the electric as per the ELV directive. So the first depolluting talks about the removal of toxic materials, airbags, and batteries. So they are clearly the batteries which is coming the major part of the electric vehicle is not taken care in the ELV. So there's the first criteria to remove the batteries and the airbags for before going for the recycling. Then going ahead, dismantling of the entire vehicle based on their material value of the aluminum or other precious material been used or steel has been used. How can be separately directly dismantling first stage, and non-recyclable part which cannot be recycled again, which will go for landfill or the energy recovery. Then is shredding, wherever whatever the cannot be dismantled easily, so it will be again completely shredding by the shredders and completely broken down into small pieces. And again, those pieces are separated out by the other mechanical process like magnetic and eddy currents and the density separators. Last one is sorting out. Again, the sorting out the all the whatever the recyclable or reusable material has been sorted out, and whatever is cannot be recycled, recovered, or the reused, that will go to the landfill. So I can say 95% of the 85 or 15% of the elements is going for the landfill or the energy recovery or the incineration in the EU. The directive majorly in European region. And there is some separate directive that they have for the batteries as well. So but the battery directive is very old, and it talks about only the minimum 50% recovery by weight for the as per the battery directive. So what the takeaway here is that need of dedicated separate guidelines for electric vehicle consideration of electric vehicle recycling, which is still in discussion. Maybe right now, though, no electric vehicle, you can say in a bulk, has been reached to that particular level, which will increase the load of the recycling. So that's why the still in discussion, but hopefully the talks is still going on. So I can say in the next slides. So right now, as per the battery directive, the it's battery there's a 2006 66 EC. So batteries, all batteries which is going maybe in EV are considered as the electric industrial batteries. There's a not separate category for the EV batteries, but it is considered industrial battery, which is same as considered as a battery used in a UPS or the normal batteries used in a vehicle, ICNG vehicle. They are considered in the same categories. And current targets for the recovery is the 65% for the lead acid battery, 75% for the nickel cadmium batteries, and 55% for the all other batteries. This is the current target has been there as per the battery directive. Further future envision is there that there's going to come up considering the EV is going to be the next battery load of batteries coming for the recycling. The lithium acid battery recycling target has been going to be revised at the 75% recovery by 2025 and 85% by 2030. And for the lithium batteries, they have targets set by 65% by 2025 and 75% by 2030. But still, it's not yet executed or deployed. It is still in discussion, still in draft stage. So what is benefit we're going to get by this new directive is that specific metal recovery targets will be 95% of the cobalt will be recovered, and 95% cobalt, copper, lead, and nickel, will be recovered, and 35% of the lithium by 2025 will be recovered. And by 2030, it will show 95% of the cobalt, copper, lead, and 75% of the lithium will be recovered. So this is become a directive, and everyone has to follow this directive and recover the whatever material. These are precious material when used for the battery manufacturing. This can be recovered, will be recovered as the battery directive will be in force. The next one is how actually the batteries be recycled in common recycling practices, which is not in very much common in India, but other countries like Europe. So they have the battery right now, as per battery directive, it's already mentioned that 50% should be recyclable. So there are four methods: the mechanical, pyrometallurgical, hydrometallurgical, and combination. Mechanical is simple method, which is the crushing, shredding of the metal, and then sorting out with the other mechanical process like magnet, eddy currents, and sieving. Highest number of benefit of this is highest number of materials recovered, but the drawback of this is for the requirement is required. This material, which is coming, recycled material, which is coming from the mechanical, cannot be directly used for the battery manufacturing. This will be contain lot of impurities in that. The next one is the pyrometallurgical. And pyrometallurgical battery process is completely battery is heated around 1500 degrees Celsius, and all the carbon content elements are burned out, and the other precious elements are taken out from this by melting it and taken out and separate it out from the process. But this process is not completely good for the environment. It contains a lot of fumes, a lot of toxic gases being involved, and so it is recommended it should not be used as a separate process. It should be used with the other process like a mechanical or hydrometallurgical, and so it will be like use a pre-treatment process for that. Third process is the hydrometallurgical process. Hydrometallurgical process, it is the battery is completely submerged in the acid and base solutions based on the properties of the elements being used, and the materials like cobalt and others been separated out with the solutions in that. So it is very efficient method, we can say, and very it's comparatively safer than pyrometallurgical, and it is as this method contains the specific acid and specific base. So the specific batteries can be recovered have the different process. Like a lead acid battery will have different acid and base solutions, and so there will be separate process for the each and every battery type, and it has a good recycling rate, and it is very material specific. And the last one is a combination. So the combination is the best method to get highest recycling efficiency here. So it can be the combination of these two: mechanical, pyrometallurgical, or hydrometallurgical. It can be combination of all three. So what is the main takeaway in this? That recycling process are evolving right now, as mentioned in the battery director as well. The 95% of cobalt, nickel, and aluminum can be recovered through these processes, and more than 80% of the lithium ion can be recovered from this recycling of the batteries. Okay, since there is again, okay, what is the impact of this recycling process? So when we're talking about the impact, what is the environmental? As I mentioned, that lot of fumes have been generated, lot of energy being used by heating the elements. So there is a lot of separate case study being conducted for separately for the recycling of the batteries. It has been conducted by the research group, and it was funded by the German Federal Ministry for the environment, natural conservation, building, and nuclear safety. So they have developed a process, and the LCA life cycle analysis study been conducted for this. And there is a framework for the life cycle analysis study, ISO 14044 and 44. So you can see on the right side there is an image called goal and scope definition, inventory analysis, impact assessment, and interpretation. So we need to define what is the goal and scope, what is our main objective to conduct a study, and what is the inventory, what are the things we are consider, what is the input, what is the output, and what is the reaction is going to happen. These all things inventory we need to consider. Impact assessment, what are the end life impact, what are the global impact, what total energy consumption, what are the total water pollution, water is required, water acidification, eutrophication. There are various impact categories are there. So it is all been decided what exactly we need to find out. And finally is the interpretation. So what we are going to achieve from this particular study. So for this particular study, it is said that they are considered the recycling of 1 ton of batteries, and which is composition of NMC, which is cathode type of a nickel, magnesium, manganese, and cobalt, and LFP, which is considered a lithium, ferrous, and phosphorus phosphates, respectively. And what is the yield of the process? What we get at the end of this process is the dilute solution of the cobalt nickel, which can be again reused for the new battery manufacturing, and other valuable elements like copper, stainless steel, plastics from the battery recycling. So what is exactly process? We'll see in the system boundary. So what is the system boundary? First of all, the system boundary is the considered in the LCA. So what are the processes we are considering for the input output of the output of the energy and the raw material, and what is the impact of the each stage. So we consider the dismantling of the battery, cell dismantling, cathode separation, and the hydrometallurgy as a process for this system boundary. So whatever the impacts is happening across these processes were considered for this particular study, and what we get out of this is a yield. As I mentioned, that production of the activated material for cathodes. So this material can be directly used for the new cathode manufacturing, which is coming from this particular recycling method. So what are the results of? Okay, we have conducted this study by this group, and what are the result of this? So this is an interesting fact we can see in this graph here. I'll just explain. First, that the GWP, the global warming potential. What we're talking about is only CO2 emissions, which is global warming potential is considered as a result as a particular impact category, and you can see the graphs here. So the 233 means the 233 grams CO2 kg of CO2 been consumed to dismantle of this particular battery, and 1965 kg of CO2 been saved because of the recovered material like stainless steel, polyamide, and other materials we are recovered from this process. So we get a credit of this recovery. So we get a credit of back. So credit means we get if you wanted to produce this raw material from the virgin, it may have some impact, right? But we are getting this material directly from the recycling, so that particular impact we have already saved, rather than buying taking it from the virgin material, we are using from recycling. So these are the credits we get for the dismantling of this particular battery. Similarly, for the other process like CDM, the seal dismantling, and other cathode separation, it is not have that much of credit. But overall, at the end of it, we get a positive. You can see the minus 1,336 kg of CO2, which is we get a good credit out of it. The environmental impact is in. I can say it is not positive impact. It's negative impact means it's good for the environment. So we are reducing the impact which is happening. It's a negative CO2 is happening in process. So we are saving a lot of CO2 while recycling and recovering the lot of elements from the recycling process. And major aspect is that we mainly we recover this precious elements like cobalt and nickel from this. And cobalt and nickel have the lot of environmental impact in their extraction, transportation stage. So we are recovering those materials, then we are saving, or we can reducing a lot of impact in that particular process. So takeaway is that the recycling gauge impact of the battery reduces the due to recycling credit dismantling. So this is the main stage where we get a lot of credits. So going ahead, what are the challenge? Okay, the battery recycling is good. We are getting a lot of credits, and it is good for the environment. But there are practical challenges also there. Practical challenges such as unorganized sector for battery recycling. There is no proper lot of challenges. There is no particular company. There are very few companies in the world. Like we are seeing that there is in US, there is Redwood Corporation, Li-Cycle, are separately batteries recycling process, but a very sophisticated and very standardized process. But if we see in the other countries like India, China, or any other African countries, the battery recycling process is very unorganized and very harmful. The next challenges is collection. The batteries which is used in EV are very heavy and very transport costly. So it's a collection and recovery of the batteries from the aftermarket. It's a big challenge. Next one is fire hazards. The battery contains lot of chemicals, lot of hazardous chemicals. So there is a lot of fire hazard. Is again a big challenge while storing of the batteries, and a serious health and environment concern to the toxic elements which is coming out of the battery. Next one is risk in handling the electrical batteries, because battery contains a huge amount of electric charge. If the battery is not properly discharged before the recycling, then there is a big chance of electrocution of people who is handling the battery. So we need to handle it very precautionally, and lot of safety has to be taken place while handling those batteries. And the safe storage also very much important. Wherever we are storing the battery, when it comes to the recycling facilities, so it has to be stored properly. It can have the lot of battery waste as well as the fire hazard. So these are the basic challenge that we have the battery recycling. So going for the motors, motor is, as I said earlier as well, the motor is easy element for the recycle. Maximum recycling can happen at the motors because of the copper, aluminum, and steel which is used, which is easily recoverable by the dismantling it. The main issue is about the recycling of the permanent magnet. So though the permanent magnet is depends upon where it is exactly placed in the motor. If it is placed at the place where it can be easily recovered, then it can be reused again. It will not lose its magnetism. As mentioned here, like magnet loses only 1% of it of magnetism and can be reused again. But case if it is been broken or surface has been damaged while dismantling or any other issues, then that magnet cannot be reused again. So the case here comes here as a recycling of these magnets. Again, these magnets contain lot of rare earth elements, which is again very scarce in the nature. So we need to make sure that recycling of these magnets happens properly. The next is power electronics. Though the power electronics, which I mentioned earlier, like DC-DC converters and all those inverters, onboard charger, not directly comes under WEEE guidelines, but it has been sold as electronic parts. So we are following the WEEE guidelines for the treatment or end of life treatment of the all electronics which has been sold. So there are the various guidelines across the world. Different countries have the different guidelines TASCA, TSCA, and regulations in the US. REACH, ROHS are regulations in Europe. IMDS is the separate guidelines that they have for material declaration and for vehicle or the automobile sector that they have. So in this process, we make sure that what are the elements as goes into the product, and their elements should be controlled at the end of its life. uh, the last treatment collection of sorting collection, sorting, and special treatment. As per this, as mentioned, that there are different 10 categories are there as per WEEE guidelines, the standard components, and there are different standard components: cable, circuit, legal, glass, mercury, battery. So there are special treatment already mentioned as per WEEE guidelines. So again, the power electronics are treated as a e-waste category as per the regulation, as per the each region. But again, the recovery of this, again, the question and sector of the e-waste I-waste recycling is again unorganized in many countries. That we need to address this. What is the impact of the untreated batteries? Okay, so we're not talking about the recycling and all, but what happens if the battery is not been recycled properly? So it will have the very adverse impact on the environment and human health. Like lithium ion battery used for the almost all the equipment we use in daily use, like mobile phones, remote, and any other equipment, like we require the small batteries. But have you think about how it has been recycled? It is right now, it is not properly the frame directive. Any penalties are there are domestic use, how the battery has been disposed. So this battery has a severe, like several toxic and flammable materials that need to be it will go for landfill. It can explode if we store it properly, not stored properly, and it can cause severe damage as well. And if it is go for landfill, it will again pollute the groundwater, and it will leach out the heavy metals, which like chromium, cobalt, copper, manganese, nickel, and this will further pollute our groundwater and soil pollution. So disposal, battery disposal of batteries end of the life to avoid harmful impact the environment. It's very important to take care of this kind of scenarios. The next solution to this. Okay, so we have a lot of recycling processes there. We need the scarcity and all. So again, the if you can see that battery is the almost 35 to 50% overall cost of electric vehicle. Battery is the costliest element or costliest part in electric vehicle. And if you see the fact at the bottom, the battery currently it is going to go up by 26%, which means the battery electric cars which we have 4,093 in 2021, which will go up to 756 by 2030. The huge number of cars are going to come up by next 10 years, and why the cars are come up, so they're going to come up in a huge demand. So the element or the raw material which is going to require for the battery manufacturer also going to go up. So this is the typical diagram. So how the lithium, nickel, cobalt source is available and how is going to meet this demand. So yellow is the demand is going to go for the electric vehicles, and this is the supply right now for these elements, which is very maybe we're going to fall short for this to provide the protocol supply for this kind of demand. And the cost of the raw material is due to the due to the high, like, first of all is the high cost of these elements also very high. It is due to the very high cost of refining and extracting those materials, as well as the transportation cost, because these are available only at the specific countries. Lithium is mainly coming from the South American countries. Cobalt is coming from the uh, DR Congo, which is conflict country again, and other elements are coming from the China, and battery itself is coming from the China, and most of the which is goes into most of the electric vehicles. So these are the monopolistic costs are going to add up the cost of the electric vehicle. So there will be further shortage. The circular economy is going to be the best solution for it. So we're going to talk about what exactly circular economy is in the future, in the next slides. Before that, okay, these are the shortages what we have discussed, supply and demand, which is going to be in the future. There are other social impacts also there in the material sourcing. If we know that the material which is coming from the which is using a battery which is coming from the countries called the Democratic Republic of Congo, there they have their own issues such as child labor, slavery, corruption, unsafe mining practices, and lot of terrorism, human rights issues. A lot of issues are there. So the materials which is already coming from this region are kind of controlled by the law called conflict minerals law. But right now, cobalt is not coming under that. But still, there are practices been followed that these practices should not be used to mine the cobalt. So, being a sensitive consumer, we should aware about cobalt is coming from this kind of practices. And also the mining and refining companies which is there in the African countries, which is again owned by the China, and they have the again monopolistic and domination in the market for the batteries cost. So this is going to be the huge which social impact which are there in the battery manufacturing. So these are the face social environmental integrity rights involving child labor, forced labor is also one of the concern. Unsafe working conditions. They are not providing any PPEs or any other equipment to protect themselves from hazardous processes. Biodiversity loss and corruption. These are the issues also there in the material resources. So how we are going to address these issues of the short demand and the social impact? So there is a concept called circular economy. So if you say the any material, if any product we consider, any product, what is the main driver of the cost of that particular product is the raw material being used. The raw material is causing a lot of main cost element of the any material, any product we purchase. And next one is the cost we also give for the wasting or the waste management of the particular product. So that is the cost and environmental implications at the which at the end of the life of the product as well. So that is the key concern for the environment. So first is the raw material which is used, and second one is the waste generation. So how we can address this? The concept is called a circular economy. Circular economy is reusing those waste again back to the product as a raw material. It's called a circular economy. So whatever the material which is coming, like earlier maybe at in case of the EV, the material is coming from the exploration, mining, processing. We are using it from the production, and we are using vehicle again reuse again and again battery, and it will finally go for the recycle. And after recycling, we'll get lot of materials back to the environment. So those recycled material can be reused again. So instead of going back to the mining efforts and extraction efforts, we can get those material right from the recycling itself. So, and we the benefit of it that we can not only reduce the cost of the raw materials, as well as we're going to reduce the environmental impacts which is happens due to the extraction of those materials. I'm going to reduce the cost of the supply chain as well. So if you see the particular circular economy, in case the electric vehicle batteries, so on the pie chart on the right side, you can see the 55% of the cost is caused by the batteries only. And battery, how we can reduce this? Followed by the motors and power electronics. How we can reduce this cost? The when recent technology, as I mentioned earlier, the 95% of the cobalt and nickel and 85% of the lithium can be recycled easily right now. Whatever the technology we have. These elements are lower. The recovering of these elements from the recycling, the cost is lower than actually buying from the raw material, by buying it from the virgin material. So these are the benefit of it, and as well as it will reduce the cost of the transportation and supply chain, and as well as the dictatorship in future may come up, like dictatorship cost is there for the fuels right now by the Gulf countries. So that also can be reduced. So we will have own controls on the cost of the material coming from the suppliers, and supplier also coming. We can have the recycling facility in the locally as well. So that will again both reduce the cost of the supply chain as well as reduce the environmental impact of the transportation. And replacing those virgin material with this recycled material, we can reduce the cost by up to 30%. And another good benefit of this, that we can reduce the disposal cost of this gate fees or disposal fees we have to pay at the end of the life of the any electric vehicle. I think you maybe all are aware that we buy any electric component or electric vehicle, the cost of the recycling of the vehicle it been already been charged to us by the registration of the vehicle. So if we in future the recycling is going to be very cheaply, and the material is very going to get recycled, that the cost of this registration maybe can go down, because this disposal cost been again finally recovered from the consumer only. So this is the way we can reduce the cost of the batteries. So again, the beautiful name for this is called the urban mining. And urban mining is a term called by the urban company here, one of the company which for the mining of this rare earth elements uh, from the electric vehicles. So generation, so how it is urban mining is called, like mining it rather than from the extraction of, or the directly from the mines, we can get the materials right from the next door recycling facilities. So the collection of collection of the batteries, separation of the magnets, neodymium batteries, and harvested from the end of life, and then sorting it out the other materials, 100% recovery of those materials, and the design again making the new products out of it and exporting for the global circular economy, and it can be used again. So this is called the urban mining concept. It's a beautiful concept which will can reduce the cost, environmental impact, and the cost of the products. What is alternate source, alternate use of the material? So okay, we know that recycling can reduce the cost, but what is the reuse of the battery, how we can do this? So right now we know that solar PVs are abundant right now. Amount of solar power is available, and it has been quite a few harnessed by the solar PV panels. Solar is available at daytime, and it is sometimes is the generation of solar power is surpassed than the requirement what we have in the daytime. So this extra power, what we can do is can we have to store it, and we can use it later in the day. So that storage is required again battery power packs. So at the end of the life of the any electric vehicles, battery is 75% of and 85% the original energy holding capacity still remains. So these reused batteries, battery from the electric vehicles can be used as a power as a captive power storage for the solar or any other electric generation power plants. So that can be stored and used again whenever we want. It's kind of modular energy storage devices, and collection of the this can be done. And some regions they are using this battery as a secondary storage at the household, as well as some of them are using this battery to power the power boards for the secondary applications. Some of the electric motor boards are there, they're powered by the used batteries coming from the electric vehicles. And there is again one of the fact mentioned here that in the US in 2017 around 45,000 EV batteries are going to be retired. So the almost 1 gigawatt hour storage capacity will be available for the state. So whatever the solar energy generation excess energy they have, they can store. Right now, the storing of this solar energy is costly affair, and it requires a lot of money. But we have the ready-made solution which is coming from the recycling of the battery, so it will be again win-win situation for the battery recycling as well as solar energy storage solutions as well. So similarly, in Eaton, we have the product called X-Storage. The X-Storage is the good product for circular economy. So it's again using for the same purpose. Like if it is the high energy generated, high solar energy generated, which is more than required, that can be stored in the X-Storage and can be used later in the day, in night time, or anywhere whenever it is required. This is a very good fact been we have seen been done by one of the customers in Norway, where we have sold at 100 kW storage there, and they have used the battery packs from the Nissan Leaf electric vehicles. So they have almost their 100 kV been complete storages. They are not using any fresh batteries. They are using the used battery from the Nissan EV. So this is the one of the good example of the circular economy, practical example of circular economy. The next one is the sustainability at Eaton. So right now we talked about what is exactly how we can do the recycling and how we can use the batteries again, and we can recover the material. So what exactly we are Eaton are doing it. So Eaton is a intelligent power management company, and we are doing the we are trying to improve the quality of life and environment of the customers. And we have the four part sustainability strategy, which address the environmental, social, and governance issue. We can see the four pillars here, like creating solutions, reducing our footprints, and doing the business right and transparency. These are the ESG issues, which are paramount issues for any company which is right now in the late global economy. Any company which cannot work only on the profits, they have to take care of their environmental issues, they have to take care of the social issues, they have to take care of the governance issue as well. So what we are Italy doing is we are doing the sustainable solutions for the customers, such as the energy transition, digitization, and electrification, and sustainable research and development practices. We are trying to reduce the footprint from our products. We have taken a science-based target as per the Paris Agreement, Paris Climate Change Agreement. We have taken a pledge to reduce the emissions from our products. We are also taking the efforts to reduce our own scope one emissions from our facilities, as well as we are targeting zero waste landfill from our facilities, and as well as zero discharge, water discharge. And also we are helping the communities to inclusion of diversity, training the people and volunteering into the in the social activities. And ethical part is very much important again as a governance part. So we are dealing with the suppliers, customers with the ethical manner, supply chain sustainable, considering sustainable supply chain wellness, and US minority and gender pay equity and governance part of it. So what we have offering in the Eaton? So as a Eaton is again one of the biggest company for the e-mobility parts suppliers. So we have the power electronics, power distribution, protection, and power systems. So we have the again DC-DC converter, DC AC inverters, onboard chargers, and we have for power distribution protections. We have the power distribution units, and for the surge of the current, we have the fuses, power circuit breakers. And again, the improving the efficiency of the electric vehicles, we have the efficient EV transmissions, and EV 48 volts mild hybrid, which will again enhance and boost the power of the electric vehicle and improve the efficiency. So these are the products that we have in our portfolio. So what are the solutions, what we are doing exactly on the to handling this end of life situations at Eaton? So we have taken goals at 2030 target till 2020. We are going to achieve this goal. So to reduce the carbon emissions from operations, the whatever the operations, the factories, manufacturing facilities that we have. So whatever the GHG emissions are occurring in our facilities, we are going to reduce it by 50% from our baseline 2018. So whatever the emissions are there at 2018, we are going to reduce by 50% till 2030. And carbon neutral operations, again reduce the carbon neutral operation means the operation will not have any CO2 emissions in at first place. Mean going for more renewable, more energy efficient productions facilities. 100% manufacturing sites will be zero waste to landfill. We are trying to recover, recycle, or regenerate all the waste we are going to generate in the factory. These are the operation level targets we are taken. And the product level for the customer solutions, again, we're creating a power management or intelligent solutions for the customers, which can be enabled them to again more go for more efficient way. And major target is again, as per the science based target, is reduce the 15% of the emissions from our products what we sold. So whatever the emissions our products are consuming, or maybe their cause of consuming the energy efficient energy or the CO2 emissions. So we are trying to reduce our emissions from our product, and we're helping the customers as well as trying to achieve our targets and increase sales from the positive impact products. So we have the category called positive impact, means our products has to be more and more sustainable solution. And that whatever products what we have positive impact, like we are considering all social impacts, environmental impacts, which is coming up because of the products. We are trying to improve sales for those particular products. So these are targets we are taken at Eaton. And what is the process that we have inside the Eaton? It's called environmental accounting, design for environment, and product stewardship. So the three main buckets how we operate here for the products. As I mentioned, it is shown in the case study for life cycle assessment. Life cycle assessment, we take care of all the aspects of we study all the aspects of the product, not only the manufacturing part of it, but the use phase part of it, how much it is efficient, where the material is coming from, how it is going to transport it. We do the complete study. We find out what are the hotspot of it. Maybe it's some particular process, a particular material is causing a lot of emission. We try to improve on it, and we give the better solution to the customers. Also, we create a handprints on how to the what is the positive. We're always trying to improve our products from the previous model what we have produced so far. So we're always trying to improve, and we have to create a difference. What is the improved product what we have, and what is different, and what is the benefit of CO2 emissions we are getting for the new developed product. So these are the main aspect of the life cycle assessment. We take a lot of do the lot of LCAs, and we find a lot of solution out of it. So how the like LCS works. So we have called a complete framework called the DFE, Design for Environment. I think you must have aware about the design for quality, design for manufacturing. So this is the same type of design for environment. So all the aspects of the design, all the aspects what we have for the environment, like LCA, product stewardship, all everything is embedded into our product development process itself. So whenever we develop any products from the start, so the DFE is one of the key attributes that everyone has to follow. Uh, all the products which we are developing has to go through the DFE lanes. They have to go through the product stewardship. They have to follow the all the regulation which is required as per the environmental regulations norms, and they have to follow the for the recyclability or the regulatory norms. And if they want to improve the focus as per the customer requirement, they want to reduce the GHG emissions of the use phase, that also will taken care of. So it is cannot be ignored. So it is completely embedded, seamlessly embedded into our product development process. So we are through this we are taking care of all the requirements which is coming from the customers, or also we are adding our own values into that. And third one is the product stewardship. Product stewardship taking care of all the environmental regulation which is there across the world, and which is will even if it is asked by the customer or not, we are taking care of the all the regulation based on where the product is going to be sold. So can it be reach or the top 65 in the US, reach in Europe, and China ROHS in the Chinese countries where the product is going to be sold. They are going to take care of all the regulations, considering all the hazardous material goes into the product. We are going to controlling or reducing it with this accordance with this particular regulations. So how, we are going again deep one step ahead. How the DFE again been processed. DFE is actually implemented in the ETAN. So the process is called product design. So first, whenever the requirements come from the customers, they come up with the core product performance or the design features. Like they wanted to improve the efficiency, they wanted to improve life, they wanted to improve the particular function of the product. So there's a main key function or key requirement which is been received from the customers. So what we do the apply the DFE toolkit to that. As per the customer's requirement, we again go through the DFE lens. So we do the life cycle assessment, we do the life cycle costing also. Life cycle costing is similar as the life cycle assessment, but it can give the hotspot where we are spending unnecessary more amount more money, those elements, those processes, those materials we can replace with the better costing solutions. Again, the circular economy, wherever we can use the reuse of material, or the material we can be easily recovered and can be recovered again for the future. And sustainable operations means the products where we are manufacturing, the operations like our own facility has to be more sustainable. It should have the good lesser GHG footprint. It has lesser waste management, better, higher efficiency. And last one is the product stewardship. Again, considering all the environmental aspects, environmental regulatory aspects, which is the product going to be sold. So we're taking the product is going to be going through this proper DFE lens, and we get the benefit. The customer gets the benefit of this particular core requirements as well as the additional requirements, and we have to find out what are the risks and trade-offs between these two, and we particularly chose this and improve our products. And what we get out of this is the improved eco design. Eco design is again the particular lanes or regulations so that we can more improved products, more environmentally sound product or a socially sound product we get out of this. Get a green marketing. We can pitch a product, or we can have the USP of product that it is more greener than earlier product. Can improve efficiency. It can reduce the waste. It can reduce the GHG emissions. So those kind of marketing also we can do. Premium pricing also we can do, because it is going to suppose it can reducing the fuel. So ultimately it's going to it's going to get a benefit to the consumer as well as the OEM. So we can sell this product with the premium pricing as well. Again, same as the low cycle cost reduction, it will help us to reduce the cost because of the life cycle costing. De-risking and future-proof product launch, and next design generation. Uh, we can consider in the whatever the next trend is coming up. Considering those targets, we can take care of all those things beforehand. So one of the example we had done is EPD. EPD is the environmental product declaration. This has been actually the declaration is considered is one of the document where all the impacts of the environment been declared at one page for the product. Like what is the impact of the GHG, what is the energy efficiency, what is the waste generation of the product. Everything is complete fully of the particular product environmental aspects are mentioned in the EPD. So we have done this is one of the example. We had a lot of products are already in place and already in progress. Also, we are working on a lot of PDs. So these are doing it. These are the things we are working on it. So what is exactly the outcome of DFE process is identify, quantify, and develop those options to mitigate the risk and enhance sustainability performance. So this is all the DFE process we have within the Eaton. So again, how we are going to enable end of life? Okay, we're talking about the main topic here is the end of life. So as I mentioned, the product stewardship is one of the main criteria. The product stewardship talks about all the regulatory aspects which is required to be followed, mandatorily followed by each country. So we have the rigorous systems for the first reach is one of the compliance for the EU. So we have a system to take care of. We take declarations, and if there is any violation is happening, we are discussing with the supplier to reduce it. And there are some 18 substances mentioned by the REACH, and it has been updated every time. So we are trying to reduce it. Lead being used. So how we can reduce the lead if it is there, and how we can reduce it by threshold limit, below the threshold limits. The cadmium again being used by the electronic components. So we are also taking care of under the ROHS regulations. And on the right hand side, you can see the end of life directive. And end of life directive is again a norm by the majorly in Europe and maybe in India as well. So we need to so there are declarations been asked by the automobile manufacturers through these regulations called GADSL and IMDS. So we declared all the material till the bottom level, what kind of material which goes into our product, and we declare it. So people or the consumers and European Union are aware what exactly will be there in my product, and they will be aware at the end of the life also what is if there is considering any hazardous material is being used or not. If it is used, then what is the special treatment for that. Similarly, for the ROHS and REACH, biocidal and persistent organic pollutants, ozone depleting pollutants have been taken care through these particular regulations. For the countries like US, there is a labeling is also one of the aspect we consider. Some components require labeling, how much chemicals, hazardous materials you have used. So it will be taken care at a later age, a later stage of at the end of the life of the product while dismantling or recycling it, and they can control the exactly the amount of which goes into that particular product. So there's a labeling also to take care. And last one is the WEEE and the WFD is a directive for the Waste Framework Directive, which will reduce the burden on the recycling of the products. And data for the SVSC means substance of very high concerns. We are also trying to restrict the substances which is used in a product. So again, the main objective of all these regulations to reduce and the impact of the hazardous chemicals, hazardous materials being used in a product at the end of the life, and you do the safe recycling of the products. So the last slide is a key takeaways what we have. So far we have talked about the how the vehicle revolutionary, electric vehicle is revolutionary and going to be the upcoming mode of transport, and it is going to help us to fight the climate change and reduce the emissions and reduce the temperature by 1.5 degree as per the climate change targets. But it comes with a lot of challenges, environmental, social benefits. So there are again solutions available that we need to implement at the deepest root. And EV space can be achieved. True sustainability can be achieved on not only thinking about manufacturing and the use phase of the part, but complete life cycle thinking is very much required by considering any solution of it, any solution of the considering the electric vehicle. So, and a sustainable end of life can be achieved through the considering all the recycling methods, options, more sustainable materials. I think right now there are a lot of technologies are being evolved. How we can reduce the dependency on the lithium, dependency on cobalt. So we can R&D is going on to reduce look for the more and more sustainable materials. And I can see the sustainable material as the recycling materials as well. And the last one is that we need a lot of good facilities and good in a set of art facilities for the recycling of these batteries and EVs, which considering safety, environment, and circulatory aspect of it. Circulatory, I mean that it should really produce a material which can directly goes into the batteries. So this is my last slide. Thank you. I'm ready to take any questions if you have.
Uh, Thank you, sir. Sir, there is one question from the participant.
Yes.
How we can overcome the unorganized sectors of battery for the recycling?
So right now the organized sector, and if you see in India, a lot of actually considering the electronic part of it, electronic aspect, electronic e-waste consider the lot of e-waste recycling happens only in Africa and Asian countries. The major reason is that the cheap labor that they have, and they can violate all the regulatory norms. But if the only one thing that it can help is to stricter environmental or regulatory norms, and more penalties on it, and more recycling facility. And majorly the recycling facilities are being developed to actually to recover the materials, the precious material like cobalt, nickel, and cobalt, nickel, aluminum, copper. Those material been majorly been recovered, and those only the aspect been take those are the only things been seen by the recyclers. So though what we can do is that rather than taking the material from raw material, if we can more approach for this recycled material, this automatically this economy will start, circular economy will start kicks off this circular economy, and it will definitely as well as the along with the regulatory and regulatory body, it can be regularized, and it can give the proper recycling facilities.
Okay, thank you, sir. Sir, can we provide any recycling certificate to the owner or any supplier?
Yes, yes. Right now, in many of the countries, like I may have mentioned, that we have the called EPDs, environmental product declarations. So, environmental product declaration in our case, like whatever products we are manufacturing, we declare the all the aspects of the environment. How much products can be recycled, how much can be recovered, or how much can be go for the landfill. So these are the certificates can be given. So while selling or manufacturing of any product, from the start itself, the consumer will know or the OEM will know how much product can be recycled or can be recovered. So those are certificates are already there. already there and provided by the many organizations. But it's kind of right now it's voluntary. It's not been regularized or it's kind of mandatory by the government or all. But yeah, in future it will be there for sure.
Okay, thank you, sir.
Yes.
So I would like to thank our today's guest speaker, Mr. Alok Bendre, sir, for sparing his valuable time for throwing lights on the post-life's impact of electric vehicle on the environment. Sir, thank you for imparting us importance of impact of electric vehicle on the environment. Also, we all are highly benefited with this knowledge and will take care and apply it in our life. Thank you, sir. So here I declare that this session is
I would
over.
like to thank everyone. I would like to thank to DY Patel all facility to give me the opportunity to present and talk about this very important topic about sustainability and become this evolving technology. It is coming with a lot of benefits. So we can how we can go more and more sustainable. So it will be definitely benefited in the future. So thank you for the opportunity. Yeah, thank you all.
Okay. At last but not least, I would like to express my sincere thanks to all participants for their valuable contribution to make this event successful. Thank you all.
Thank you very much.
I declare that this session is over. Okay. Tomorrow we will again meet at 4 p.m. Thank you.